There's something out there in space that shouldn't exist. Planets so light, so fluffy, that they defy everything we know about how planets are supposed to work. Imagine a world the size of Jupiter, but so lightweight that it could float in water, if you could find a cosmic ocean big enough. Scientists call them superpuffs, and they might just be the weirdest planets ever discovered. But here's the thing, nobody knows how they formed, why they exist, or what they're even made of. And the more we learn about them, the more confusing they become. Superpuffs break all the rules. Normally, planets follow a pattern: small rocky planets close to their stars, big gas giants farther out. But these? They don't fit anywhere. They're massive, yet barely there. If you could stand on one, you'd probably sink right through the atmosphere before ever finding solid ground. But here's the real mystery: how do they even stay together? How do they exist in a universe where the laws of physics should have crushed them into something denser? And what if these strange, ghostly planets are hiding secrets that could completely change how we understand the formation of worlds? To figure this out, we need to go deep into the science, the theories, and the mind-blowing discoveries that have left astronomers scratching their heads. Because superpuffs aren't just rare. They might be telling us something big, something we've completely missed about how planets form, what they're made of, and maybe even how life itself could exist on worlds that seem impossible. So let's dive in. First, let's talk about what these planets actually are. The term superpuff was first used to describe a handful of exoplanets, planets outside our solar system, that were found to have incredibly low densities. We're talking densities lower than cotton candy. These planets are about the size of Jupiter or Neptune, but their mass is shockingly low. If you compare them to the gas giants in our solar system, they don't make any sense. Jupiter, for example, is mostly made of hydrogen and helium, but it's incredibly dense because of the immense gravity crushing everything inward. Superpuffs, on the other hand, are somehow resisting that compression, staying so light that they seem almost hollow. The first real evidence of these strange worlds came from NASA's Kepler Space Telescope. Kepler was designed to hunt for exoplanets by looking for tiny dips in a star's brightness when a planet passes in front of it. It was great at finding planets, but when it found superpuffs, scientists were completely baffled. They weren't just low density. They were so extreme that some of them seemed physically impossible. One of the most well-known superpuffs is a planet called Kepler 51d. This thing is huge, almost the size of Jupiter, but its density is so low that it's almost like a giant ball of fog. If you could scoop up a piece of it, it would feel lighter than air. Kepler 51d and its sibling planets in the same system, Kepler 51b and Kepler 51c, are some of the puffiest planets ever discovered, and they've been a complete nightmare for scientists trying to explain them. So how did they get this way? That's the big question. One theory is that these planets formed much farther out in their solar systems, where ice and gas could build up without being stripped away by their stars. Then, at some point, they migrated inward, but they never became denser. Another idea is that they have incredibly thick atmospheres full of hydrogen and helium, making them look bigger than they actually are. But here's the catch: those atmospheres should have been stripped away by their stars a long time ago. So why are they still so inflated? Some scientists think superpuffs might actually be in a temporary state, something that won't last forever. Maybe they started off as normal gas giants but got hit by something massive that fluffed them up. Or maybe they're still young, and over millions of years, their atmospheres will shrink down into something more normal. But that brings up another mystery. If superpuffs are just a phase, why have we found so many of them? Shouldn't they be rare? And here's where things get even weirder. Some researchers have suggested that superpuffs might actually be hiding something inside, like a solid core surrounded by an atmosphere so thick and extended that it tricks us into thinking the whole planet is made of air. If that's the case, what's inside those atmospheres? Could there be clouds of exotic elements, or even some form of unknown chemistry we've never seen before? The Hubble Space Telescope has tried to get a closer look at these planets, analyzing the light that passes through their atmospheres. But instead of finding clear chemical signatures, Hubble hit a wall, literally. The atmospheres of superpuffs seem to be filled with something that blocks light in a way we don't fully understand. It's almost like they're wrapped in a thick, high-altitude haze that prevents us from seeing what's really going on beneath. What is that haze made of? Could it be a form of alien weather? Something completely different from clouds on Earth, Jupiter, or even Titan. Some scientists think these planets might have incredibly deep atmospheres that stretch for tens of thousands of kilometers, with bizarre weather patterns unlike anything in our solar system. Imagine clouds made of compounds we've never seen, storms that last for centuries, and winds so fast they could rip apart anything that tried to land there. Superpuffs could be entire worlds of mystery, hiding chemistry and physics that break everything we thought we knew about how planets work. But the biggest mystery of all? We don't know how many of them are out there. We've only scratched the surface, and as telescopes get better, we might find that superpuffs aren't rare at all. What if they're actually common, and we just haven't been looking the right way? What if there are entire solar systems filled with planets that are so light, they're like giant balloons floating in space? And if they're common, then what does that mean for life? Could life exist on a planet that's mostly air? What would that even look like? Could superpuffs be home to strange, floating organisms, drifting in the thick, alien atmosphere, surviving off the chemistry of the clouds? Or could they be completely uninhabitable, their atmospheres so unstable that nothing could ever survive there? We don't know yet. But what we do know is that superpuffs have already changed the way we think about planets. They prove that the universe is far weirder than we ever imagined, and they remind us that no matter how much we think we understand, space will always find a way to surprise us. The more we study these bizarre planets, the more questions arise. For example, if superpuffs are so light and fragile, how do they even survive? Space is an incredibly hostile place. Planets are constantly bombarded by radiation, hit by asteroids, and pulled up by the immense gravitational forces of their stars. A planet as delicate as a superpuff shouldn't last long, yet here they are. One theory is that their atmospheres are somehow replenishing themselves over time. Maybe they're constantly pulling in gas from space, balancing out the loss caused by their star's radiation. If that's true, then what kind of process is keeping them so inflated? Is there some kind of hidden mechanism inside these planets, something we've never seen before? Could it be that superpuffs have an internal heat source that keeps their atmospheres expanded, like a balloon being constantly refilled with air? Then there's another puzzle. How do superpuffs even form in the first place? When we look at our own solar system, we see a clear pattern. Rocky planets like Earth and Mars formed closer to the Sun, where it was too hot for gas giants to form. Jupiter and Saturn, being much farther out, were able to accumulate massive amounts of hydrogen and helium, turning into the dense, compact gas giants we see today. But superpuffs? They don't fit into that pattern at all. Some scientists believe they may have started out much farther from their stars, where conditions were right for them to form as huge, puffy worlds. But over time, their orbits changed, bringing them closer to their stars. This would explain why many of the superpuffs we've found are relatively close to their host stars. But that explanation creates another problem. If they moved closer, why didn't their atmospheres get stripped away? Why didn't they shrink down into something more like Neptune? There's also the possibility that superpuffs formed in a completely different way than other planets. Maybe they didn't build up from small bits of rock and ice like Earth and Jupiter did. Maybe they were born from a different kind of cosmic process, one that we don't yet understand. And then there's the weirdest question of all. What if superpuffs aren't planets at all? What if there's something else entirely? Some scientists have suggested that they might actually be failed stars, objects that tried to ignite into full-blown stars but didn't have enough mass to make it happen. Instead of becoming stars, they just ended up as huge, airy balls of gas, floating through space without the heat and energy to shine. If that's the case, then superpuffs might be a missing link between planets and stars, an in-between stage that we've never fully recognized before. Could it be that these worlds are telling us something new about how solar systems form? Could they be remnants of a failed star system, leftovers from a process that almost, but not quite, created a second sun? And what about their atmospheres? We already know that planets in our own solar system have incredibly diverse atmospheres. Venus has thick clouds of sulfuric acid, Jupiter has raging storms of ammonia, and Saturn's moon Titan has rivers of liquid methane. So what could be lurking in the atmospheres of superpuffs? Could they have elements and compounds that don't exist anywhere else in the universe? Some scientists have suggested that their atmospheres might be rich in exotic gases, things we've never seen before on Earth. These gases could be responsible for keeping them so inflated, acting like some kind of cosmic insulation that prevents them from collapsing into denser worlds. But if that's true, then why haven't we seen those gases anywhere else? What if the chemical makeup of superpuffs is so different from anything we know that it completely changes our understanding of planetary science? And let's take this idea even further. If their atmospheres are made of something completely unique, could they be harboring entirely new forms of weather? Imagine storms that don't rely on water or wind, but instead are driven by forces we can't even comprehend. Could there be slow, rolling currents of dense gas that act like massive, invisible rivers flowing across these planets? Could there be weather cycles that operate on timescales of thousands of years, storms that have been raging since the birth of the planet itself? And here's another mind-blowing thought. What if these planets are actually evolving? We tend to think of planets as static objects, things that form and stay the same for billions of years. But what if superpuffs are still changing, still going through some unknown transformation process? What if they're in the middle of becoming something else, something we haven't even imagined yet? That brings us to the ultimate question: could life exist on a superpuff? At first glance, it seems impossible. These planets don't have solid surfaces, so there's nowhere for life to take hold in the way it does on Earth. Their atmospheres are so thick and extended that any form of life would have to exist entirely in the sky. But here's the thing, we already know of life forms on Earth that don't need solid ground. Take a look at Earth's own atmosphere. There are microorganisms that survive in the upper layers of our planet's sky, floating on air currents and feeding on microscopic particles. Could something similar exist on superpuffs? Could there be life forms that have adapted to living in the dense, swirling atmospheres of these strange worlds? And if they do exist, what would they look like? Would they be massive, balloon-like creatures drifting on the winds? Would they be microscopic, living in dense clouds of exotic gases? Could they have developed completely new ways of surviving, feeding off the chemical reactions in their strange, puffy atmospheres? The truth is, we have no idea. But the more we study superpuffs, the more we realize that the universe is far stranger than we ever imagined. These planets defy our understanding, challenge our theories, and force us to reconsider everything we thought we knew about how worlds are born and evolve. And here's the craziest part. We've only just begun to scratch the surface. Our current telescopes can only tell us so much, and the data we have is limited. But with the next generation of space telescopes, like the James Webb Space Telescope, we'll be able to study these planets in more detail than ever before. We might finally get answers to some of the biggest mysteries surrounding superpuffs. Or, just as likely, we might discover something even stranger, something that completely rewrites our understanding of planets, atmospheres, and even life itself. Because if superpuffs can exist, what else is out there? What other impossible worlds are waiting to be discovered? If superpuffs exist in multiple star systems, then that raises another question. Are they a rare anomaly, or have we just never looked closely enough? Right now, we classify planets based on what we already know, comparing them to the ones we've seen before. But what if superpuffs are actually more common than we think? What if there are countless other star systems out there filled with planets just like these, planets that don't follow any of our existing rules? And if we do find more of them, what patterns will emerge? Will they all be found close to their stars, or will we start to see them scattered throughout different regions of space? If they're all in similar orbits, that could suggest they formed under specific conditions we don't yet understand. But if they're spread out everywhere, then that could mean they're a natural stage of planetary evolution, something that might even happen to other gas giants over time. Think about Jupiter. Right now, it's a massive, dense gas giant with a thick atmosphere. But what if, billions of years ago, it was something more like a superpuff? What if, At one point in its history, it was just as light and airy as the exoplanets we're studying now. Could it be that all gas giants go through an early, puffy, phase before they settle into their final forms? If that's true, then what we're seeing with these exoplanets isn't just a rare phenomenon, it's a glimpse into how planets grow and change over time. But if that's the case, what happens next? Do superpuffs eventually shrink down into normal gas giants? Do they collapse in on themselves, their atmospheres pulled in by gravity until they become dense like Jupiter and Saturn? Or do they stay the way they are forever, drifting through space as giant, low-density worlds? And here's something even weirder. What if superpuffs don't shrink, but instead expand even further? What if, over billions of years, they continue to grow, their atmospheres spreading out even more until they become something entirely new? Could there be planets out there so massive and diffuse that they blur the line between planet and star? That idea might sound crazy, but it's not as far-fetched as you might think. Astronomers have already discovered objects known as brown dwarfs, bodies that are too big to be planets, but not big enough to be stars. They're often called failed stars, because they don't have enough mass to ignite nuclear fusion. But what if superpuffs represent the opposite end of that spectrum? What if they're planets that are growing outward instead of inward, becoming something completely different from anything we've ever seen before? And if that's possible, then what does it mean for the future of planetary science? Right now, we think of planets as distinct objects with clear categories: rocky, gas giant, ice giant. But what if the reality is much more fluid? What if planets can shift from one type to another, evolving over time in ways we've never considered? The more we study superpuffs, the more they force us to question our assumptions. Every planet we've discovered so far has fit into a category that makes sense, until now. Superpuffs don't belong to any of our established models, and that means one thing: we have to rethink everything. Maybe our definition of a planet is too narrow. Maybe we've been so focused on what we know that we've ignored the possibility that planets can exist in forms we've never imagined. And if that's true, then what other surprises are waiting for us out there? Because here's the biggest mystery of all: if superpuffs can exist, what else is lurking in the vastness of space, beyond the reach of our current technology? What kinds of planets have we not yet discovered? What kinds of worlds are waiting for us, hidden in the shadows of the universe? The existence of superpuffs makes one thing clear: our understanding of planet formation is still incomplete. The very fact that these planets exist means there are processes happening in the universe that we haven't accounted for. And if superpuffs challenge our current models, what other planetary types might be out there, defying everything we think we know? Consider this: when the first exoplanets were discovered, many of them were hot Jupiters, massive gas giants orbiting extremely close to their stars. At the time, scientists thought this was an anomaly, something rare. But as more exoplanets were found, it became clear that hot Jupiters were actually quite common. The same could be true for superpuffs. Right now, they seem unusual, but what if they're just the tip of the iceberg? What if space is filled with planets that break all the rules? If that's the case, then how many other planetary classes remain undiscovered? We assume planets must be either rocky, gaseous, or icy. But what if there are planets made entirely of liquid, held together by a delicate balance of gravity and atmospheric pressure? What if there are worlds composed of exotic materials, substances so strange that they don't even exist naturally on Earth? Superpuffs force us to expand our imagination. They exist in a zone between what we expect and what we can't yet explain. And when you find something in science that doesn't fit into your current theories, it means one of two things: either you're missing a key detail, or your entire theory needs to be rewritten. So what if our models of planetary formation need a complete overhaul? Right now, we assume that planets form in a simple, predictable way, starting as dust and gas, clumping together into solid bodies, and either remaining rocky or accumulating enough material to become gas giants. But what if that's just one of many possible paths? What if superpuffs represent an entirely separate branch of planetary evolution? Some scientists have even speculated that superpuffs might not be planets at all, at least not in the traditional sense. Instead, they could be remnants of failed star formation, objects that almost became stars but didn't quite make it. If that's true, then they might have more in common with brown dwarfs than with planets like Jupiter or Neptune. And that raises another question: what happens to superpuffs over time? If they're incredibly low density, does that mean they're stable, or are they in a state of constant change? Could their atmospheres slowly dissipate over billions of years, leaving behind a rocky core? Or could they collapse in on themselves, shrinking into denser planets as they lose their outer layers? If superpuffs do change over time, then what we're seeing right now might just be a snapshot of a much longer process. Imagine if planets could transform from one type to another, starting as superpuffs, then evolving into gas giants, then eventually shrinking down into something else entirely. If that's true, then planetary classification isn't as simple as we thought. Instead of fixed categories, planets might exist on a spectrum, shifting between different forms over billions of years. And if that's the case, what does it mean for planets in our own solar system? Could Jupiter have once been a superpuff? Could Neptune be in the process of shrinking into something denser? Could there be a stage of planetary evolution that we've completely overlooked because we've only ever studied the planets in our own backyard? Superpuffs don't just challenge our understanding of exoplanets. They force us to rethink the very nature of planets themselves. They show us that the universe is far more complex than we ever imagined. And perhaps most importantly, they remind us that for every question we answer, a dozen more arise in its place. Because if superpuffs exist, what else is out there, waiting to be discovered? Superpuffs have shaken the foundation of planetary science, but the deeper we dig into their mysteries, the more questions we uncover. These incredibly low-density exoplanets force us to reconsider not just how planets form, but also what a planet can even be. They challenge our definitions, break our models, and stretch the limits of our understanding in ways that few other discoveries have. If planets can exist with the density of cotton candy, what else could be out there? Are there planets that defy even more of our expectations? And could superpuffs be a missing link in some grander cosmic puzzle that we haven't even begun to grasp? One of the strangest aspects of superpuffs is their atmospheres. Normally, a planet's atmosphere is determined by its gravity, temperature, and composition. On Earth, for example, gravity is strong enough to hold onto a thick atmosphere, but not strong enough to trap lighter gases like hydrogen and helium over long periods. Gas giants like Jupiter, on the other hand, are massive enough that they can keep hold of these lighter elements, forming enormous, dense atmospheres. But superpuffs seem to break this rule. They have incredibly extended atmospheres, yet their gravity is much weaker than expected for their size. How is that possible? One possibility is that superpuffs are experiencing extreme atmospheric inflation. The heat from their parent stars might be puffing up their atmospheres, causing their gases to expand far beyond what we would normally expect. But that explanation has some problems. For one, not all superpuffs orbit extremely close to their stars. Some are located in regions where the temperature shouldn't be high enough to cause this kind of extreme expansion. So if heat isn't the main factor, what else could be at play? Another theory is that superpuffs are composed of materials that are much lighter than we've ever encountered in planetary science. What if their cores are not made of the typical rock and metal found in most planets, but something entirely different? What if they contain substances with ultra-low density, possibly even unknown elements or exotic compounds? Could there be forms of matter that exist only in the extreme conditions of space, materials that behave in ways we can't yet predict? If so, then superpuffs could be a sign that our understanding of planetary composition is incomplete. But here's where things get even stranger. Superpuffs might not be solid planets at all. Some scientists have proposed that they could be gigantic, loosely bound collections of gas, more like failed stars than traditional planets. If that's the case, then they might be evolving over time, slowly collapsing in on themselves as they lose mass to space. Imagine a planet-sized cloud of gas, barely held together by its own weak gravity, drifting through space and constantly changing shape. If we could watch a superpuff over millions or billions of years, what would we see? Would it shrink down into a denser gas giant? Would it dissolve completely, leaving nothing behind? Or could it transform into something entirely new? And what if superpuffs represent just one stage in a much larger planetary life cycle? We assume that planets stay relatively stable over time, but what if that's not the case? What if planetary evolution is far more dynamic than we ever imagined? Could gas giants like Jupiter and Saturn have once been superpuffs? Could there be a future where Neptune's atmosphere expands, turning it into a new kind of superpuff billions of years from now? If planets can change their fundamental structure over time, then what other surprises are waiting for us? There's also the question of how superpuffs form in the first place. Traditional planet formation models struggle to explain them. Normally, planets form from the gradual accumulation of dust and gas in a protoplanetary disk. Rocky planets form when solid materials clump together, while gas giants form when a rocky core gathers enough gas to create a thick atmosphere. But superpuffs don't fit neatly into this model. If they have large atmospheres, then they should have massive cores, yet their densities suggest they don't. So how did they end up with so much gas? Could they have formed in an environment unlike anything we've ever observed? One possibility is that superpuffs formed in a region of space with an unusually high concentration of lightweight gases. If they formed in a gas-rich disk, they might have been able to collect huge atmospheres without needing a dense core. But that raises another question. Why haven't we found more planets like this? If superpuffs formed in a unique environment, does that mean those conditions no longer exist? Could they be relics from a time when the universe was different, a time when planetary formation followed rules that no longer apply? Another theory suggests that superpuffs might not have formed where we see them today. Instead, they could have started in a completely different part of their solar systems, and then migrated to their current orbits. If they originally formed much farther out from their stars, in cold, gas-rich regions, then they might have been able to accumulate their massive atmospheres before drifting inward. But that idea comes with its own problems. If they moved closer to their stars over time, why didn't their atmospheres evaporate? And if they formed farther out, why don't we see more planets like them in those distant regions? The more we learn about superpuffs, the more they defy explanation. They don't fit into our models, and every new discovery raises more questions than answers. But that's exactly what makes them so exciting. Science advances when we find things we don't understand, when we're forced to question our assumptions and rethink everything we thought we knew. Superpuffs are a reminder that the universe is far more complex than we ever imagined, and that we're only just beginning to scratch the surface of its mysteries. And if planets like superpuffs exist, then what else is out there, waiting to be discovered? Could there be planets even stranger than these, worlds with properties so bizarre that they challenge the very definition of what a planet is? Could there be planets made entirely of gas with no solid core at all? Could there be planets with atmospheres so thick that they blur the line between a planet and a star? Could there be planets with densities even lower than superpuffs, planets so light that they're on the verge of drifting apart? Superpuffs are not just a curiosity. They are a sign that the universe is far more diverse than we ever imagined. They prove that planetary formation is not as simple as we once thought, and that there are still fundamental gaps in our knowledge. But perhaps most importantly, they remind us that space is filled with surprises. Every time we think we have the answers, the universe throws something new at us, something that forces us to think bigger, to look deeper, to question everything. And that's what makes space exploration so incredible. We are constantly standing at the edge of the unknown, pushing forward into a universe that refuses to be predictable. With every new exoplanet we discover, we get one step closer to understanding the bigger picture. And yet, for every question we answer, 1,000 new mysteries emerge. So the question is, what's next? If we've already found planets that seem impossible, what will we find in the future? As our telescopes improve, as we send new missions into space, as we develop better methods of studying distant worlds, what other secrets will we uncover? And when we finally unlock the mysteries of superpuffs, will we be left with satisfying answers? Or will we find ourselves facing even bigger questions? Because if the history of space exploration has taught us anything, it's this: the universe is never what we expect. And the more we learn, the more we realize just how much we still don't know. If superpuffs are already rewriting our understanding of planets, then what does that mean for everything else we thought we knew about the cosmos? These incredibly lightweight, oversized worlds don't just exist in isolation. They are part of a much larger story, a narrative of planetary evolution, cosmic diversity, and the fundamental nature of matter itself. Their existence forces us to ask whether the categories we use to define planets, stars, and everything in between are even accurate. And if we are struggling to classify these worlds, then what else are we missing? Let's take a step back. The traditional models of planetary formation tell us that planets start as small rocky or icy bodies, gradually accumulating mass through collisions and gravitational attraction. If they reach a certain size, they can begin capturing gas from the surrounding protoplanetary disk, forming thick atmospheres. This is how gas giants like Jupiter and Saturn are believed to have formed. But there's a problem. Superpuffs don't follow this pattern. Their density is so low that they don't seem to have the massive cores required to attract such enormous atmospheres. And yet, here they are, existing in multiple star systems, completely defying our expectations. One of the biggest mysteries is their stability. If a planet has a thick atmosphere but very little gravity, shouldn't that atmosphere just drift away into space? Normally, a planet's ability to retain gas depends on its mass and temperature. Hot, low-mass planets tend to lose their atmospheres over time as the gas particles reach escape velocity and drift into space. But somehow, superpuffs have managed to hold on to their vast, fluffy atmospheres despite their low density. That means something else must be at play. Could magnetic fields be involved? On Earth, our magnetic field protects our atmosphere from being stripped away by the solar wind. Could superpuffs have extraordinarily strong magnetic fields that help them retain their atmospheres? If so, that would mean their interiors must be generating some kind of dynamo effect, which in turn suggests they must have at least some kind of dense core or metallic elements. But if they do have a core, why is their overall density still so low? Are we missing something about how planetary interiors work? Another possibility is that superpuffs are much younger than we think. If they are still in an early stage of their evolution, then their extended atmospheres might be a temporary phenomenon. Maybe they are in the process of shrinking down, their atmospheres slowly contracting as they cool over time. If that's the case, then superpuffs might not be a permanent planetary type at all, but rather a short-lived phase in the life cycle of certain exoplanets. If we could observe them over millions or billions of years, would they eventually settle into more familiar forms, becoming gas giants or even rocky worlds? Or would they dissipate entirely, leaving behind only a trace of their former selves? And then there's an even weirder idea. What if superpuffs aren't planets at all? What if they are something entirely different, something we haven't even considered yet? Could they be remnants of failed stars, objects that started forming like brown dwarfs but never quite reached the mass needed for fusion? Could they be the collapsed remains of once larger celestial bodies, stripped of their outer layers in some cataclysmic event? Or could they be artificial? Could an advanced alien civilization have engineered them for some unknown purpose, shaping their structures in ways that defy natural explanations? The alien hypothesis might sound extreme, but when we're dealing with objects that already break all known rules, every possibility has to be considered. If a civilization had technology advanced enough to manipulate planetary atmospheres, they could theoretically construct a world that looks just like a superpuff. Perhaps they would do this to create habitable zones in otherwise inhospitable star systems. Or maybe they would use them as energy harvesting stations, their thick atmospheres acting as giant heat-trapping blankets. While there's no direct evidence to support this idea, it's a reminder that when we find something this strange, we have to keep an open mind. There's also a deeper, more fundamental mystery at play here. Superpuffs may hold clues about the very nature of matter itself. Our understanding of atomic structure and planetary composition is based on the behavior of elements under normal conditions. But what if, in the extreme environments of deep space, matter behaves differently? What if the building blocks of these planets are subject to forces or interactions that we don't yet understand? Could there be new states of matter, exotic particle interactions, or quantum effects that allow these worlds to exist in a way that shouldn't be possible? One area of research that could provide answers is the study of exoplanet atmospheres. By analyzing the light that passes through a planet's atmosphere, scientists can determine its composition and structure. If we could get a clearer picture of what superpuffs are made of, we might finally start to unravel their secrets. But here's the catch. Many of these planets have atmospheres that are so thick and hazy that they are incredibly difficult to study. Their very nature makes them elusive, preventing us from easily deciphering their properties. It's almost as if they are hiding their secrets, teasing us with just enough information to make us curious, but never enough to fully understand them. The more we look at superpuffs, the more they challenge us. They don't fit into our existing categories, they don't behave the way planets are supposed to, and they open up a Pandora's box of new questions. But that's exactly why they are so important. Every major breakthrough in science starts with something that doesn't make sense. When we find something that contradicts our models, we are forced to refine those models, to look deeper, to explore new possibilities. Superpuffs might just be the key to unlocking a whole new understanding of planetary science, and maybe even physics itself. And this is just the beginning. As our telescopes improve and we discover more superpuffs, we will start to see patterns. Are they all made of the same materials? Do they all exist in similar types of star systems? Do they evolve over time? And most importantly, are there even stranger planets out there, waiting to be found? Because if the universe has already given us planets as bizarre as superpuffs, then what else is lurking in the vastness of space? Could there be planets that are even lighter, even more extreme? Could there be worlds with densities so low that they are barely distinguishable from interstellar clouds? Could there be planets made entirely of unknown elements, or ones that exist in states of matter we haven't even discovered yet? The truth is, we are only just beginning to explore the diversity of exoplanets. Every time we think we've seen it all, the universe surprises us with something new. And as long as there are mysteries like superpuffs out there, we will keep searching, keep questioning, and keep pushing the boundaries of what we thought was possible. Because the universe isn't just vast, it's filled with the unknown. And the unknown is where the most exciting discoveries are waiting to be made. If superpuffs are just one of the many strange planetary types that exist, then what does that tell us about the sheer variety of worlds out there? These planets have already proven that our previous understanding of planetary formation was too limited. But they also suggest that we might be missing entire categories of planets, worlds that exist in ways that defy our expectations. Imagine if superpuffs aren't an anomaly, but rather just the first step toward discovering something even stranger. Maybe they represent an entire class of planets that form under extreme conditions, in environments we haven't yet considered. Perhaps they are the missing link between gas giants and something even more bizarre, planets that are so diffuse they barely qualify as solid objects, or worlds that exist in a semi-fluid state, constantly shifting and reforming. What if there are planets out there that don't even have a true surface, but instead exist as massive clouds of material, held together by forces we don't fully understand? And then there's the question of how these planets interact with their surroundings. We already know that planets can influence their star systems in unexpected ways. A planet's gravity can affect the orbits of its neighbors, its magnetic field can shape the behavior of surrounding space, and its atmosphere can interact with solar radiation in ways that create entirely new phenomena. But superpuffs, with their massive atmospheres and low density, could be interacting with their environments in ways we haven't even considered. Could they be absorbing energy from their stars in a way that makes them expand rather than shrink? Could they be acting as cosmic sponges, pulling in stray particles and gases from their surroundings, constantly growing and evolving? Could they even be influencing the very structure of their star systems, subtly altering the formation of other planets, or affecting the behavior of distant comets and asteroids? And what about their atmospheres? If superpuffs have such thick, extended atmospheres, then what exactly is inside them? Are they filled with exotic gases, compounds that don't exist on Earth, or even elements that we haven't discovered yet? Could their atmospheres contain strange weather patterns, massive storms that stretch across their entire surfaces, or cloud formations that behave in ways we can't predict? Could they even support some form of alien life? Perhaps not life as we know it, but something entirely different, something that thrives in the dense, gaseous environments of these strange worlds? If we ever want to answer these questions, we need better observations. Right now, our understanding of exoplanets is still limited by the technology we have. We can detect their size, their mass, their density, and sometimes their atmospheric composition. But we can't yet see them up close. We don't have detailed images, and we can't send probes to explore them. We are still working with incomplete data, making educated guesses based on what little information we have. But that is about to change. With the next generation of telescopes, we are going to get a much clearer picture of these strange planets. Instruments like the James Webb Space Telescope and future space-based observatories will allow us to study exoplanet atmospheres in unprecedented detail. We will be able to detect specific molecules, analyze their temperatures, and even look for signs of complex chemistry. And with future advancements, we might even be able to take direct images of these planets, revealing their structures in ways we never thought possible. And when that happens, who knows what we will find? Will we discover that superpuffs are just the beginning? Will we uncover planets that are even lighter, even more extreme? Will we find worlds that challenge not just our understanding of planets, but of physics itself? Because that's the thing about space. It's always full of surprises. Just when we think we have the answers, the universe throws us a new mystery. And superpuffs are just one of the many questions that remain unanswered. Superpuffs are already strange enough, but the real mystery is what they could be hiding. With such thick, extended atmospheres, their cores remain completely obscured. We don't know if they have rocky surfaces, liquid interiors, or something far weirder. Some researchers even speculate that they might not have traditional cores at all, just vast regions of compressed gases slowly swirling at their centers. If that's true, then it would mean these planets exist in a state that is almost incomprehensible. Instead of being a solid object wrapped in gas, a superpuff could be something more fluid-like, constantly shifting, never truly stable. And if that's the case, what happens over time? Do these planets collapse in on themselves? Do they eventually lose their atmospheres and shrink into something more familiar? Or do they continue expanding until they reach some breaking point we don't yet understand? And then there's the possibility that they aren't even naturally occurring in the way we assume. Could some external force have shaped them? Could they be remnants of once larger planets that were stripped of their denser material, leaving behind only the lightest gases? Could they be failed gas giants, planets that started to form like Jupiter or Saturn but never accumulated enough mass to fully develop? Or perhaps they are even stranger than that. Some theories suggest that certain types of planets could act as natural, bubble worlds, places where unusual physical forces balance out in ways we don't typically see. In extreme conditions, gravity, pressure, and radiation could interact in ways that allow for planets that don't fit any of our existing categories. Superpuffs might be the first evidence of such a phenomenon, hinting at entire new classes of celestial objects that we haven't yet identified. And if there are superpuffs, could there be the opposite? Could there be ultra-dense planets, worlds that are the same size as Jupiter but weigh far more, compressing matter to extreme levels? If so, could those planets be hiding black hole-like properties, gravity so strong that even light behaves strangely around them? Could they be so dense that their very existence defies our understanding of how matter should behave? These are the kinds of questions that push the boundaries of what we think we know. They force us to reconsider not just how planets form, but how the universe itself operates. If superpuffs exist, then they must have formed somehow. And if they formed, then there must be processes at work that we haven't accounted for. What if they are tied to something even bigger? Could they be linked to the missing mass of the universe? We know that dark matter exists, but we don't know what it is. Could superpuffs interact with it in ways that other planets don't? Could their strange densities be a sign that they are somehow entangled with unseen forces? Or could they be remnants of something ancient, planets left over from a time when the universe was vastly different, operating under conditions that no longer exist? Maybe they are fossils of a forgotten era, showing us glimpses of physics that were once common but have since disappeared. And this is why we need to study them. Because every time we find a new mystery like this, it isn't just about one strange planet or one weird anomaly. It's about everything we don't yet know. Superpuffs might be the key to understanding something fundamental about the universe, something we've overlooked because we never thought to look in the right place. Imagine what could happen if we discover even more of them. Right now, we've only found a handful. But what if there are thousands? What if there are entire systems filled with them, places where these strange planets are the norm rather than the exception? And what if, just what if, somewhere out there, there's one that isn't empty? One that isn't just a ball of gas, but a place where something exists, something alive? Because if there's one thing the universe keeps teaching us, it's that the impossible has a way of becoming reality. And superpuffs? They're just the beginning. Superpuffs are already rewriting the rules of planetary science, but the real question is, what else are they hiding? If planets like these exist, then what does that mean for the broader structure of planetary formation across the galaxy? These strange, ultralight worlds shouldn't exist based on what we currently understand, and yet, there they are, floating in space, defying expectations. Their existence challenges the models we've built, forcing us to rethink everything from the way planets grow to the way atmospheres evolve over time. But if we take a step back and look at the bigger picture, the true implications become even more staggering. What if superpuffs aren't just an anomaly, but part of a much larger, hidden pattern? Right now, we categorize planets based on mass, size, and atmospheric composition, but what if that framework is too limited? We've already had to create entirely new classifications for exoplanets, like hot Jupiters, mini Neptunes, and super-Earths, because reality keeps proving that our assumptions were too narrow. So what if there are entire classes of planets out there that we haven't even considered yet? What if superpuffs represent just one small glimpse into a much deeper, more complex planetary landscape? Take a moment to imagine the possibilities. We're used to thinking of planets as either rocky, like Earth and Mars, or gaseous, like Jupiter and Saturn. But what if there are planets that blur the lines between these categories? What if some planets have vast, gaseous envelopes like superpuffs, but with molten or metallic cores so small that they barely register? Or what if some planets are even less dense than superpuffs, so diffuse that they almost behave like giant, self-contained clouds drifting through space, held together only by weak gravitational forces? Could there be planets made almost entirely of vapor, with no solid surface at all? And if planets like that exist, how do they interact with their environments? One of the biggest mysteries surrounding superpuffs is how they hold onto such massive atmospheres without losing them to space. Traditional models suggest that planets this light should be stripped bare by the intense radiation from their host stars. So how do they maintain their vast, extended atmospheres? Could there be some unknown process at work, some kind of shielding effect, or an interaction with their magnetic fields that prevents atmospheric loss? Or could it be that superpuffs aren't stable at all? Could they be temporary, transient objects, planets caught in an in-between state, slowly losing mass over time? Maybe they started off as larger, denser worlds, but some catastrophic event stripped away their heavier elements, leaving only the lightest gases behind. If that's true, then superpuffs could represent a brief phase in a planet's evolution, a stage that only lasts for a few million years before they eventually shrink or dissipate entirely. But if superpuffs are temporary, then what happens to them next? Do they collapse under their own weight, condensing into something more like Neptune? Or do they break apart, scattering their atmospheres into space and leaving behind only a small, rocky core? Could they eventually become something even stranger, like rogue planets drifting through the galaxy, their structures forever altered by whatever process created them? And what about their chemical compositions? We've detected hints of hydrogen and helium in their atmospheres, but that barely scratches the surface. What if their thick, extended clouds contain complex organic molecules, or even exotic elements that we haven't discovered yet? If conditions within these atmospheres allow for unique chemical reactions, then they might hold clues about the origins of life itself. Some scientists speculate that gas giants could serve as chemical factories, producing compounds that could later seed other planets with the building blocks of life. Could superpuffs be playing a similar role, acting as cosmic laboratories for the formation of complex chemistry? And then there's the truly mind-bending possibility. What if some of these planets are actually artificial? That might sound like science fiction, but consider this. Superpuffs exist in a mass range that shouldn't naturally allow for such enormous atmospheres. If we discovered one in our own solar system, we'd immediately assume something was strange about it. So what if some superpuffs aren't naturally occurring, but are instead the remnants of massive, abandoned megastructures, artificial shells built by ancient civilizations, now slowly collapsing under the weight of time? If an advanced civilization ever wanted to create a lightweight, habitable environment in space, a superpuff-like structure might be one way to do it. The thick atmosphere could act as a natural radiation shield, protecting inhabitants from cosmic rays while maintaining a relatively stable internal climate. Over time, if the civilization abandoned the structure or it lost whatever energy source was sustaining it, the entire thing might start to collapse, eventually resembling a natural planet. Could some of these objects be the decayed remnants of something like a Dyson sphere, or the failed attempts of an ancient race to create floating cities in space? And what if they're still inhabited? If life does exist on superpuffs, it would have to be something completely unlike anything we know. With such low gravity and thick atmospheres, life on these planets would likely evolve to be lightweight, potentially even airborne. Could entire ecosystems exist within these deep, cloudy layers, with organisms adapted to floating in the dense gases, feeding off the complex chemistry in the air? Could there be creatures drifting through the skies of a superpuff, never needing to land because there is no true surface to land on? The more we study planets like these, the more we realize how little we actually know. Superpuffs are not just another category of exoplanet. They represent a challenge to everything we thought we understood about planetary science. They prove that the universe is far stranger than we ever imagined, and they hint at possibilities that we are only beginning to explore. And if something as bizarre as a superpuff can exist, then what else is out there? What other planetary mysteries are still waiting to be discovered? Could there be planets that are even more extreme, planets made entirely of liquid, or planets with atmospheres so thick that they behave more like oceans? Could there be planets where gravity is so weak that objects float effortlessly, or worlds where the entire surface is covered in permanent, planet-wide storms? And what about the planets we haven't even thought to look for yet? Right now, our ability to detect exoplanets is limited by our technology. We can only see planets under specific conditions, when they pass in front of their stars, or when their gravity subtly influences nearby objects. But what if there are planets that don't fit those criteria? What if there are entire classes of celestial objects that remain invisible to us simply because we haven't developed the right tools to find them yet? This is why studying superpuffs is so important. They aren't just a curiosity, they're a sign that our models of the universe are incomplete. Every time we find a planet that defies expectations, it forces us to expand our thinking, to question what we assume is possible. And if history has taught us anything, it's that the universe is always one step ahead of us, always waiting to reveal something that we never saw coming. So as we continue searching the cosmos, looking for new worlds and new mysteries, one thing is certain: superpuffs are just the beginning. And whatever comes next might change everything we thought we knew about the nature of planets, the structure of the universe, and perhaps even the origins of life itself. The implications of superpuffs stretch far beyond just their classification as planets. Their existence challenges the way we think about planetary formation, evolution, and even the limits of what's physically possible in the cosmos. If such low-density planets exist, then what does that mean for our broader understanding of the universe? Could there be even stranger planetary types that we haven't yet detected? Are there other objects that bend the rules of physics in ways we've never considered? One of the biggest mysteries surrounding superpuffs is their formation. Traditional models of planet formation suggest that planets start as small rocky or icy cores, which then gather gas and dust over time. This process, known as accretion, typically leads to a steady increase in density as the planet gains more material. But superpuffs don't follow this pattern. Instead, they have massive, bloated atmospheres that seem to have formed in a way we can't yet explain. One possibility is that they formed much farther from their stars, where gas was more abundant, before migrating inward to their current positions. If this is the case, then their extreme low density could be a result of forming in a colder environment, where volatile gases like hydrogen and helium were more easily captured. But if that's true, then why don't we see more of these objects? If superpuffs were a natural product of planetary migration, we should be detecting them more frequently. Instead, they seem to be rare anomalies, suggesting that something unusual must have happened during their formation. Another theory suggests that they may have once been more massive planets that somehow lost most of their heavy material, leaving only their giant gas envelopes behind. If this is the case, then what kind of event could strip a planet of its denser layers while leaving its atmosphere intact? Could they have suffered massive collisions that blew away their rocky cores? Or were they once part of a larger system, where interactions with other planets, or their star caused them to shed their mass over time? If superpuffs are losing mass, then that raises another major question: how long do they last? Are we witnessing them at a specific, temporary phase in their existence? Could they eventually shrink, collapsing under their own gravity as their atmospheres dissipate into space? Or do they remain in this strange, bloated state indefinitely, defying the normal rules of planetary evolution? Their atmospheres are another puzzle. Some observations suggest that their clouds could be made of exotic compounds, possibly even materials that don't exist in large quantities on Earth. Could these thick atmospheres contain elements or chemical interactions that we've never seen before? If their atmospheres are stable, what prevents them from escaping into space? And if they do slowly dissipate, what does that process look like? Could we be witnessing the slow death of a planetary type that we previously didn't know existed? There's also the question of temperature. Some superpuffs orbit relatively close to their stars, meaning their atmospheres should be exposed to intense radiation. In most cases, planets exposed to such conditions would lose their atmospheres over time. But superpuffs seem to hold on to theirs, suggesting that there might be unknown atmospheric processes at play. Could their thick clouds be acting as a shield, reflecting radiation in a way we haven't accounted for? Or could their magnetic fields, if they have any, be playing a role in preserving their atmospheres? And what if superpuffs aren't just a rare anomaly, but instead represent an early stage in planetary evolution that we just haven't recognized before? Could they be a missing link in our understanding of how planets develop over time? If they do eventually shrink, then they might be a crucial phase in the life cycle of many planets, one that we're only now beginning to observe. If that's the case, then what does it mean for planetary diversity across the universe? Could it be that many of the planets we currently classify as something else, Neptunes, gas dwarfs, or even rogue planets, were once superpuffs in their early stages? Could this be a universal stage of planetary evolution that happens more often than we realize, but we just haven't been looking for it? And then there's the most intriguing possibility of all. Could some superpuffs harbor life? We often associate the potential for life with planets that have stable surfaces and liquid water. But what if life doesn't need a surface at all? On Earth, we already see microbial life thriving in the upper layers of our atmosphere, surviving in conditions once thought to be too extreme. So what if superpuffs, with their thick, gas-heavy atmospheres, have evolved their own forms of airborne life? If they do, then what would that life look like? Would it be microscopic, similar to bacteria and fungi that float in Earth's atmosphere? Or could it be something larger, perhaps vast, jellyfish-like organisms that drift through the thick clouds, feeding off chemical reactions in the air? If life has adapted to these extreme conditions, it might be unlike anything we've ever imagined, rewriting our understanding of where and how life can exist in the universe. The discovery of superpuffs is a reminder that the universe is far stranger than we ever expected. These planets don't just challenge our understanding of exoplanets. They force us to reconsider the very nature of planetary formation, evolution, and habitability. They suggest that our models might be incomplete, that there are forces at work in planetary science that we still don't fully understand. And if something as bizarre as a superpuff can exist, then what other strange planets are out there, waiting to be discovered? Could there be even larger, even less dense planets that make superpuffs look ordinary by comparison? Could there be planets that are almost entirely made of gas, with no solid core at all? Could there be exoplanets so vast and diffuse that they stretch the very definition of what a planet is? Every new discovery in space expands the limits of what we think is possible. Just a few decades ago, we didn't even know that exoplanets existed. Now, we've found thousands, and each new one forces us to rethink our assumptions. Superpuffs are just the latest mystery, but they won't be the last. As our technology improves, we'll be able to study these planets in greater detail, analyzing their atmospheres, their compositions, and their histories. And as we do, we may find answers to some of these questions, or we may find even more mysteries that we never expected. But one thing is certain: the more we learn about the universe, the more we realize how little we actually know. Superpuffs are a glimpse into a cosmic landscape filled with wonders we're only beginning to uncover. And whatever secrets they hold, they remind us that space is still full of surprises, waiting for those who are bold enough to keep searching. Superpuffs are a testament to how little we truly understand about planetary diversity in the universe. They sit on the very edge of what we thought was possible, defying expectations in almost every way. Their incredibly low density, thick atmospheres, and unknown formation mechanisms challenge the very foundations of planetary science. But they also open the door to even more fascinating possibilities, some of which could completely rewrite what we know about planets, atmospheres, and even the conditions necessary for life. One of the biggest mysteries surrounding superpuffs is their stability. How do these planets maintain such a low density without collapsing under their own gravity? The sheer size of their atmospheres suggests that they should be unstable, vulnerable to being stripped away by solar winds or disrupted by gravitational interactions. And yet they persist. Could it be that there is some unknown process at play, keeping these planets from losing their atmospheres over time? Some scientists speculate that superpuffs may have unusually strong magnetic fields that help protect their atmospheres. On Earth, our magnetic field plays a crucial role in shielding our planet from solar radiation, preventing the atmosphere from being eroded by the constant bombardment of charged particles from the sun. If superpuffs have strong magnetic fields, they might be able to hold on to their atmospheres much longer than we would expect. But this raises an even bigger question: how would a planet with such low density generate a strong magnetic field in the first place? Most planets with strong magnetic fields, like Earth and Jupiter, have dense, metallic cores that create a dynamo effect. This effect occurs when molten metal moves within the planet's interior, generating electric currents that produce a magnetic field. But superpuffs, with their extremely low density, are unlikely to have such a core. If they don't have a traditional metallic core, then how could they produce a magnetic field strong enough to protect their atmospheres? One possibility is that superpuffs might have an internal structure unlike anything we've seen before. Instead of a solid, well-defined core, they could have a diffuse, cloud-like interior with multiple layers of gas and plasma interacting in complex ways. If these interactions create strong electrical currents, they might generate a magnetic field through an entirely different mechanism, one that we don't yet understand. Another major puzzle is the composition of their clouds. Observations suggest that their atmospheres may be made up of exotic compounds, potentially including substances that don't exist naturally on Earth. Could these thick clouds be composed of elements or molecules that behave in completely unexpected ways? If so, then what kinds of chemistry might be happening in their atmospheres? Could these chemical reactions play a role in keeping the planet stable, preventing their atmospheres from dissipating? Some researchers have even proposed that superpuffs could be undergoing a slow but steady process of atmospheric renewal, where gas is somehow being replenished rather than lost. If this is true, then where is this gas coming from? Could superpuffs have internal reservoirs of volatile materials that continuously release gases into their atmospheres? Or could they be pulling in material from their surroundings, capturing hydrogen and helium from space and using it to maintain their bloated size? The existence of superpuffs also raises broader questions about the diversity of exoplanets in general. If planets like these can exist, then what other strange worlds might be out there? Could there be even lower density planets, with atmospheres so thick that they resemble miniature stars more than planets? Could there be planets that are almost entirely composed of gas, with no solid surface at all? And what about their potential for hosting life? If superpuffs have stable, thick atmospheres, then it's possible that they could have conditions suitable for some form of life, especially if their atmospheres contain the right mix of elements and energy sources. We already know that life on Earth can thrive in extreme environments, from deep-sea hydrothermal vents to the upper layers of the atmosphere. So what if life has evolved to exist in the thick, swirling clouds of a superpuff? If life does exist in these atmospheres, it might look nothing like anything we've ever seen before. It could be airborne, drifting on the winds like massive floating organisms, or it could exist as microscopic entities suspended in the dense gases. The chemistry of these planets could allow for entirely new biochemical processes, potentially leading to life forms that are completely alien to us. But even if superpuffs don't host life, they still force us to rethink what's possible in the universe. Every new discovery in exoplanet science expands the boundaries of our understanding, revealing that the cosmos is far more diverse and complex than we ever imagined. Superpuffs might be rare, or they might be part of a larger category of planets that we just haven't identified yet. Either way, they represent a mystery that demands further investigation. As our telescopes and observation techniques improve, we will be able to learn even more about these strange planets. The upcoming James Webb Space Telescope and other future missions will allow us to analyze their atmospheres in greater detail, searching for clues about their composition, formation, and evolution. And with each new piece of data, we will get closer to understanding the true nature of superpuffs, and perhaps uncover even more bizarre and unexpected worlds in the process. But one thing is certain: the more we explore space, the more we realize that the universe is full of surprises. Superpuffs are just one example of how reality can defy our expectations, challenging us to think bigger and question everything we thought we knew. And if these strange, low-density planets can exist, then what else is out there, waiting to be discovered? The mystery of superpuffs doesn't just stop at their structure and composition, it extends to their very origins. How do planets like these even form? Traditional models of planetary formation struggle to explain how a planet could end up with such an enormous atmosphere relative to its core. Did these planets form farther away from their stars and then migrate inward, capturing extra gas along the way? Or did they form in place under unusual conditions that we have yet to understand? One theory suggests that superpuffs might have started out as ice-rich planets that later accumulated thick atmospheres of hydrogen and helium. If they formed in the colder regions of their solar systems, they could have gathered large amounts of ice and other volatile materials, which later vaporized as they moved closer to their stars. This could explain their extreme puffiness. If their interiors were originally composed of frozen water, ammonia, or methane, those materials could have expanded significantly as they warmed up, creating the bloated planets we see today. However, this idea comes with problems. For one, if superpuffs did migrate inward from colder regions, then we would expect to see other planets in similar orbits with similarly low densities. But so far, superpuffs appear to be relatively rare, suggesting that whatever process created them is not a common one. Additionally, if their puffiness is due to heating, then they should be losing their atmospheres over time, gradually shrinking down as their gases escape into space. Yet, they appear to remain stable, which means there must be something else at work. Another possibility is that superpuffs formed in extremely gas-rich environments, where the normal balance of planetary formation was disrupted. In a typical solar system, gas and dust swirl around in a protoplanetary disk, gradually clumping together to form planets. But if the gas in the disk was unusually thick, it might have allowed some planets to accumulate much more of it than usual, forming giant atmospheres around relatively small cores. This could explain why superpuffs exist, but it raises another question: why don't we see more of them? Could it be that superpuffs are simply a temporary phase in planetary evolution? Perhaps they are young planets that have not yet finished settling into their final forms. Over time, they might lose their outer layers, shrinking down into denser, more typical planets. If this is the case, then we might be witnessing a rare transitional stage in the life cycle of certain exoplanets, one that only lasts for a relatively short period before the planets become something else entirely. Another wild idea is that superpuffs could be the remnants of past cosmic events, such as planetary collisions or failed attempts at star formation. If a massive impact stripped away the outer layers of a gas giant, leaving behind only a puffy core, it might resemble what we see in superpuffs today. Or if a small star failed to ignite and instead collapsed into a planet-like object, it might have ended up with an extremely low density. While these ideas are purely speculative, they highlight just how little we know about these strange worlds. The more we study superpuffs, the more questions arise. Their existence challenges not just our models of planet formation, but also our understanding of atmospheric physics, magnetic fields, and even planetary evolution. They are so unlike anything in our own solar system that every new discovery about them forces us to reconsider what is possible in the universe. One of the most exciting aspects of studying superpuffs is that they push the limits of our technology. Because their atmospheres are so large, they provide an excellent opportunity to study planetary atmospheres in detail. When a superpuff passes in front of its star, light from the star filters through its atmosphere, allowing astronomers to analyze the composition of its gases. This method, known as transmission spectroscopy, is one of the most powerful tools we have for studying exoplanets. With upcoming telescopes like the James Webb Space Telescope, we will be able to get even more detailed measurements of these planets. By studying their atmospheres, we might be able to determine what kinds of elements and molecules exist within them, which could give us crucial clues about their origins. Could superpuffs have exotic chemical compositions, unlike anything found in our solar system? Could they contain traces of organic molecules, hinting at the possibility of life? If we ever find signs of biological activity in the atmosphere of a superpuff, it would be one of the most groundbreaking discoveries in the history of science. Life, if it exists on these planets, would have to be adapted to extremely unusual conditions, floating in thick clouds of hydrogen and helium, possibly relying on completely unknown biochemical processes. It would be unlike anything we have ever seen before. Even if life is unlikely on these planets, superpuffs are still important for understanding the broader picture of planetary science. They show us that the universe is far more diverse than we ever imagined, full of strange and unexpected worlds that challenge our assumptions. If planets like these can exist, then what else might be out there, waiting to be discovered? Could there be even more extreme planets, with even lower densities or even stranger atmospheres? The study of superpuffs is just beginning, and every new piece of data brings more surprises. As we continue to explore the cosmos, we may find answers to some of the biggest questions about these planets, or we may find even deeper mysteries waiting for us. One thing is certain, the universe is far stranger than we ever imagined, and the discovery of superpuffs is just one small glimpse into the vast, unknown possibilities that lie beyond our solar system. Superpuffs represent one of the most perplexing puzzles in exoplanet science, but their implications stretch far beyond just planetary formation. They force us to rethink the very physics governing planetary atmospheres, the limits of what a planet can be, and even how we define a planet in the first place. With densities comparable to cotton candy, these celestial objects defy our traditional classifications. Are they failed gas giants? Are they planets still in the process of forming? Or could they be something entirely different, something we haven't yet conceived of? One of the strangest things about superpuffs is their surprising stability. Given their extreme puffiness, one might expect them to be highly unstable, with their atmospheres gradually leaking away into space. Yet they seem to persist over millions or even billions of years. This raises a crucial question: what is holding these atmospheres in place? One possibility is that superpuffs have incredibly strong magnetic fields, which help protect their atmospheres from being stripped away by stellar winds. If this is the case, then their internal structures must be very different from what we expect. Strong magnetic fields typically require a liquid metallic core, like Earth's iron-nickel core or Jupiter's deep hydrogen layers. But with such low densities, it's unclear whether superpuffs even have the internal pressure needed to create these magnetic fields. If they do have strong magnetism, then it means our understanding of how magnetic fields are generated needs to be re-examined. Another explanation could be that superpuffs contain a large amount of complex molecules or exotic gases that make their atmospheres more resistant to evaporation. For example, if they contain significant amounts of molecular hydrogen mixed with heavier compounds, the interactions between these gases might create a kind of self-shielding effect, preventing them from easily escaping into space. If this is true, then studying superpuffs could help us understand more about atmospheric chemistry and how planets maintain their atmospheres over long periods. There's also the possibility that superpuffs are surrounded by vast, unseen rings or debris clouds that make them appear larger than they really are. Some scientists have proposed that the measurements of superpuffs' densities might be misleading because what we're actually observing is not just the planet itself but also a huge disk of material surrounding it. If this is the case, then superpuffs might not be as extreme as they seem, but that would still be a major discovery because it would suggest that large ring systems around exoplanets are more common than we thought. Even more fascinating is the idea that superpuffs might not be fully solid planets at all, but rather a strange intermediate state between planets and stars. Some researchers have speculated that under the right conditions, a large gas-dominated body could form that is either a full-fledged gas giant nor a rocky planet, but something in between, a kind of failed star that never quite gained enough mass to ignite nuclear fusion. This would place superpuffs in an entirely new category of celestial objects, potentially leading to a complete overhaul of how we classify planets. The mystery deepens when we consider the sheer rarity of superpuffs. Despite the thousands of exoplanets discovered so far, only a handful of them fit into this ultra-low-density category. This suggests that whatever process creates superpuffs is not a common one, or that these planets do not survive for long before transforming into something else. If we could determine what makes superpuffs different from other planets, we might gain insight into the hidden processes that shape planetary systems across the galaxy. One of the most exciting aspects of studying superpuffs is the opportunity they provide for understanding atmospheric escape, how gases leak away from a planet over time. This is crucial for understanding not just exoplanets, but also the history of our own solar system. For example, Mars likely had a much thicker atmosphere in the past, but it lost most of it due to solar wind stripping. If superpuffs can maintain their huge atmospheres despite their low gravity, then they must have mechanisms preventing atmospheric loss that we don't yet understand. Unraveling this mystery could give us new insights into planetary habitability, helping us determine which exoplanets are most likely to retain atmospheres suitable for life. Speaking of life, could superpuffs be home to some form of exotic life? At first glance, their extreme conditions seem inhospitable. Their thick hydrogen-dominated atmospheres, combined with low surface gravity, would make them very different from Earth-like planets. However, some astrobiologists have speculated that certain kinds of microbial life could potentially exist in the upper atmospheres of such planets, floating in dense clouds of gas. If this is possible, it would mean that the search for life in the universe needs to expand beyond just Earth-like planets and consider entirely different types of environments. As more advanced telescopes come online, we will get better and more detailed data on superpuffs. Instruments like the James Webb Space Telescope, JWST, are expected to provide high-resolution spectroscopic data, allowing us to analyze the exact composition of these planets' atmospheres. If JWST detects unexpected elements, it could radically change our understanding of how planets form and evolve. We might discover unknown chemical reactions occurring in their atmospheres, or even new physical processes that challenge the laws of planetary science as we currently understand them. There is also the possibility that some superpuffs could eventually collapse in on themselves, compressing into denser forms over time. If they are losing their atmospheres at a slow rate, then they could be undergoing a gradual transition from puffy gas planets into rocky super-Earths or Neptune-like worlds. If this hypothesis is correct, then superpuffs might not be a permanent type of planet but rather a brief stage in planetary evolution that we are lucky to be observing at this moment in cosmic history. The study of superpuffs is still in its early stages, and with every new discovery, the mystery deepens. These strange, oversized planets may hold the key to answering some of the biggest questions about exoplanets, atmospheric physics, and even the fundamental processes that govern planetary formation. The more we learn about them, the more we realize just how much we still don't know about the universe. What other surprises might be hiding out there among the stars? Could there be even stranger planets that we have yet to discover, worlds that defy the very laws of physics as we know them? If superpuffs exist, then what else is possible? The universe is vast, full of secrets waiting to be uncovered, and every new mystery we solve only leads to more questions. The journey to understanding these strange planets is far from over. In fact, it may just be beginning. The enigma of superpuffs doesn't just challenge our understanding of planetary science, it forces us to reconsider the very fundamentals of matter, density, and atmospheric dynamics. When we look at these impossibly light planets, we're staring at objects that shouldn't exist under conventional astrophysical models. And yet they do. The more we learn about them, the more they seem to defy explanation, hinting at hidden forces, unknown compositions, or entirely new categories of planetary evolution that we haven't yet considered. One of the most mind-boggling aspects of superpuffs is how they manage to retain such massive atmospheres while orbiting relatively close to their host stars. Under normal circumstances, a planet with such low gravity should struggle to hold on to its gases, especially if it's being bombarded by stellar radiation. The solar winds, magnetic fields, and extreme heat from their stars should strip these planets down over time, leaving behind only a dense core. But somehow, superpuffs maintain their enormous, fluffy atmospheres for millions, perhaps even billions, of years. This suggests that something is actively keeping their gases from escaping. One leading hypothesis involves an unexpected chemical composition. Perhaps these planets are not made of the materials we typically associate with planetary atmospheres, such as hydrogen, helium, and carbon dioxide, but instead contain exotic gases that interact in ways we don't yet understand. If superpuffs are rich in elements that create a kind of self-insulating effect, their atmospheres might be far more stable than expected. Some researchers speculate that they could have high concentrations of methane, ammonia, or even unknown compounds that form ultralight but persistent cloud layers, shielding the planet from atmospheric loss. Another possibility is that these planets are much younger than we think, and we just happen to be observing them at a brief stage in their development. If superpuffs are newly formed worlds, they may still be in the process of cooling and settling, which could explain their unexpectedly low densities. In this scenario, they might eventually shrink as their atmospheres condense or escape, transforming into more familiar types of exoplanets over time. If true, then superpuffs could represent a missing link in planetary evolution, a glimpse into the chaotic early stages of planet formation that we rarely get to witness. Yet, the idea that they are simply young doesn't quite fit all the observations. Many of the known superpuffs exist in relatively mature star systems, meaning they must have been around for a long time. If they were going to shrink, they should have done so by now. This means that their puffiness must be a stable feature, not a temporary phase. And that only deepens the mystery. One of the most bizarre theories suggests that superpuffs might be something completely different from what we assume. What if they aren't planets at all? Some astronomers have considered the possibility that these objects could be remnants of ancient failed stars. Perhaps the lingering cores of gas giants that lost their outer layers due to some past cataclysmic event. If a massive gas giant was stripped of most of its atmosphere in a violent collision, it could leave behind an unusually low-density remnant, one that still holds onto a thin but expansive shell of gas. Alternatively, they might be what some call dark planets, worlds composed largely of exotic materials like dark matter or strange quark matter, which would give them unique properties that defy standard planetary models. While this idea is highly speculative, it's not entirely out of the question. If dark matter interacts with normal matter in unexpected ways, it could form structures that appear planet-like but behave very differently from anything we've seen before. Another perplexing aspect of superpuffs is their interaction with their host stars. Unlike gas giants, which tend to have well-defined atmospheric layers, superpuffs appear to be in a state of constant flux, their outer layers shifting and changing as they orbit. Some researchers suspect that these planets may experience extreme atmospheric tides, meaning that the gravitational pull of their stars literally stretches and compresses their atmospheres in a way that makes them appear even larger than they really are. If this is happening, then their true sizes might be much smaller than current estimates suggest, and their densities could be higher than we think. On top of that, some superpuffs have unusual orbital patterns, suggesting that they might have formed in one location and then migrated to their current positions. If this is the case, then their original environments could have been vastly different from where they are now. Perhaps they formed in colder, more distant regions of their star systems, where lower temperatures allowed them to accumulate massive atmospheres before moving inward. If so, then they could be relics of a lost era in their planetary system's histories, preserving conditions that no longer exist in their current orbits. The search for more superpuffs is ongoing, and with each new discovery, we get closer to understanding what they really are. Future telescopes like the Extremely Large Telescope, ELT, and upcoming space missions will provide even more detailed data, allowing us to analyze their atmospheric compositions in ways never before possible. If we can determine what gases they contain, how they interact with their stars, and whether their densities change over time, we may finally unlock their secrets. But for now, superpuffs remain one of the greatest enigmas in modern astronomy. They exist at the very edge of what we consider possible, challenging our understanding of planetary physics, atmospheric chemistry, and even the fundamental rules of how matter behaves in space. Every new observation brings more questions than answers, and as we continue to study these ghostly, oversized worlds, we may find that they hold the key to some of the deepest mysteries of the cosmos. The deeper we dig into the mystery of superpuffs, the more we realize that these planets don't just challenge one aspect of planetary science. They challenge nearly everything we thought we knew about how planets form, evolve, and maintain their atmospheres. Every assumption we've made about planetary density, atmospheric retention, and composition seems to be defied by these bizarre, balloon-like worlds. One of the strangest things about superpuffs is that they orbit relatively close to their stars. Normally, a low-density planet would struggle to survive in such an environment. The intense radiation should be stripping away its atmosphere at an alarming rate. Yet, somehow, these planets persist, maintaining their enormous, extended atmospheres despite being bombarded by stellar winds. This alone suggests that something unusual is happening with their atmospheric composition or the way their magnetic fields interact with their parent stars. One possibility is that superpuffs have extremely strong magnetic fields that help shield their atmospheres from solar radiation. If their cores generate powerful magnetic fields, these could act as protective bubbles, preventing charged particles from stripping away the planet's gases. However, if that were the case, we would expect to see clear signs of strong magnetospheres, such as intense auroras or interactions with their star's stellar winds. Yet so far, we haven't found any definitive evidence of such effects. Another idea is that their atmospheres are composed of an unusual mix of gases that make them far more resistant to evaporation than we'd expect. Hydrogen and helium are the lightest and most easily stripped away, but what if superpuffs contain something different? Some researchers suggest that these planets might have thick layers of methane, ammonia, or even exotic compounds that interact with radiation in a way that helps them retain their gaseous envelopes. Perhaps they have high-altitude cloud layers that reflect much of the incoming radiation, reducing atmospheric loss over time. But even if we assume that their atmospheres are somehow stable, we still have to explain how they became so puffy in the first place. Planets don't simply inflate without a reason. For a world to maintain such a low density, it must have either formed in a unique way or undergone some dramatic transformation that changed its internal structure. One of the most radical ideas suggests that superpuffs might not be what we think they are at all. Instead of being fully formed planets, they could be in the middle of a slow but inevitable collapse. If these planets formed in a colder region of their star systems and then migrated inward, they might have originally contained a much higher proportion of volatile ices, things like water, ammonia, and methane. As they move closer to their stars, these ices would have started to sublimate, turning into gases and expanding the planet's overall volume. If this process is still ongoing, then what we're seeing could be a temporary phase, one where the planets appear much larger than they truly are due to their extended, evaporating atmospheres. This idea leads to another intriguing possibility. What if superpuffs are actually failed ice giants? If you take a planet that was originally meant to become a Neptune-like world but never quite gained enough mass, you might end up with something that looks very similar to a superpuff. These planets might have started as normal gas or ice giants, but lost a significant portion of their atmospheres due to some unknown event. Perhaps a past collision, a nearby supernova, or an unstable phase in their star's early history. The remnants of these disrupted worlds could still be floating in space, masquerading as ordinary planets when in reality, they are something entirely different. Yet another possibility is that superpuffs are the result of planetary mergers. If two smaller planets collided in the past, their combined mass might have created a new world with a large, extended atmosphere. If this happened relatively recently on cosmic timescales, then the atmosphere might not have had time to fully settle, leaving behind a planet that appears abnormally puffy compared to its peers. This could explain why some superpuffs are found in multi-planet systems, where gravitational interactions between planets make collisions more likely. But perhaps the most mind-bending theory of all is that superpuffs might be artificial. What if, instead of being natural planets, these objects are actually gigantic megastructures built by an advanced alien civilization? Some scientists have speculated that highly advanced beings could construct lightweight, balloon-like structures in space, perhaps as enormous habitats or as components of a massive energy-harvesting system. If a civilization had the technology to engineer ultralight, gas-filled structures on a planetary scale, they could create something that looks exactly like a superpuff from a distance. While this idea is highly speculative, it's worth considering simply because superpuffs are so unlike anything else we've ever seen. Regardless of their true nature, one thing is clear: superpuffs represent one of the biggest puzzles in exoplanetary science. They force us to question our assumptions about planetary formation, atmospheric physics, and even the fundamental nature of matter itself. The more we study them, the more they challenge us, and with every new observation, we uncover more questions than answers. As next-generation telescopes come online, including the James Webb Space Telescope and future ground-based observatories, we'll be able to analyze these planets in unprecedented detail. By studying their atmospheric compositions, their thermal properties, and their interactions with their host stars, we may finally begin to unravel their secrets. But until then, superpuffs remain one of the most baffling and fascinating mysteries in the universe. Superpuffs are not just strange outliers in our database of exoplanets. They are forcing us to rethink the very foundation of planetary science. Every discovery related to these bizarre, oversized worlds raises new questions that challenge our understanding of how planets form, evolve, and interact with their environments. It's almost as if nature has placed these planets in our sights specifically to keep us humble, reminding us that the cosmos is far more complex than we ever imagined. One of the most perplexing aspects of superpuffs is how they managed to form in the first place. Standard planet formation models struggle to explain how a planet can accumulate so much gas without also accumulating a significant amount of rock and metal. Typically, gas giants form by first building up a large rocky core, which then attracts and holds onto a massive atmosphere of hydrogen and helium. But superpuffs seem to have skipped this step. They have the atmospheres of gas giants, but lack the expected dense cores that should be lurking beneath the clouds. This raises the question: did superpuffs form through an entirely different process than other planets? One possibility is that they formed much farther from their stars in a region rich in icy material, where their atmospheres could expand more freely due to lower gravity and pressure. If they later migrated inward, their atmospheres might have remained extended due to some unknown stabilizing factor. This would imply that there are many more of these planets out there, possibly lurking in the outer reaches of other star systems, waiting to be discovered. But if migration were the answer, then why don't we see more examples of planets transitioning from superpuffs to more compact worlds? If a superpuff were gradually losing its atmosphere due to stellar radiation, we should be able to observe cases where the process is halfway complete. Planets that still have large atmospheres but are clearly shrinking over time. So far, we haven't found a single exoplanet that fits this description, suggesting that whatever process keeps superpuffs inflated is not as simple as atmospheric loss. Another intriguing theory suggests that superpuffs might be held together by exotic forms of matter. Some researchers have speculated that these planets could contain large amounts of dark matter, which would alter their gravitational properties in ways that make them appear more inflated than they actually are. If dark matter can somehow interact with normal matter inside these planets, it might create a strange balance where the planet's size remains large despite having relatively little mass. While this idea is speculative, it does highlight just how desperate scientists are to find an explanation that makes sense. There's also the possibility that superpuffs are not planets at all, but rather massive collections of loosely bound debris. If these planets are made up of fluffy, porous material rather than solid rock, their densities could be much lower than expected. Imagine a giant cosmic sponge, absorbing gas and dust from space but never becoming dense enough to collapse into a solid body. If this is the case, then superpuffs might be temporary structures, unstable clouds of material that will eventually break apart or collapse into more traditional planets. One of the most exciting prospects in studying superpuffs is the opportunity to analyze their atmospheres in greater detail. The James Webb Space Telescope, JWST, has already begun collecting data on some of these worlds, using infrared spectroscopy to determine what kinds of gases make up their atmospheres. Early results suggest that some superpuffs have high-altitude clouds made of unknown materials, further deepening the mystery. Are these clouds responsible for keeping the planets inflated? Could they be composed of exotic compounds that behave differently from anything we've seen before? The idea that superpuffs could contain unknown chemical processes is particularly exciting because it opens the door to the possibility of entirely new forms of planetary chemistry. If these planets are made of substances that don't exist on Earth, or that exist in only trace amounts, we could be looking at the first evidence of alternative chemical pathways that only occur in extreme cosmic environments. This could have implications not just for planetary science, but for our understanding of chemistry and physics on a fundamental level. But perhaps the most mind-blowing possibility is that superpuffs could be early-stage gas planets that never fully formed. If these planets were once on the path to becoming full-fledged gas giants but were somehow halted in their growth, we might be witnessing a rare snapshot of planetary evolution in action. This could provide crucial insights into how Jupiter-like worlds develop and why some planets end up as gas giants while others remain rocky. Superpuffs challenge our ideas about how planetary atmospheres work, how planets gain and lose mass, and even what it means to be a planet in the first place. They remind us that for all our technological advancements, we are still at the very beginning of our journey to understand the universe. Every answer we find leads to new questions, and every new discovery forces us to rethink what we thought we knew. As we continue studying these enigmatic worlds, we may find answers that reshape our understanding of planetary science, or we may uncover even deeper mysteries that defy explanation. But one thing is certain, superpuffs are not just strange planets. They are cosmic riddles, waiting to be solved. And the more we learn about them, the more we realize just how little we truly know about the universe. Superpuffs are not just a curiosity. They could be a missing piece in our understanding of planetary formation, evolution, and even the broader structure of exoplanetary systems. The more we study them, the more they defy conventional logic, suggesting that the processes that shape planets are far more diverse and complex than previously imagined. Every time scientists think they are on the verge of an answer, new data emerges that forces them to reconsider their theories. One of the most perplexing aspects of these planets is their sheer fragility. With densities comparable to cotton candy, it's difficult to imagine how they could survive for millions or even billions of years. The extreme radiation from their host stars should be stripping away their atmospheres at an alarming rate, yet they remain intact. This suggests that either they are continuously replenishing their atmospheres in a way we don't yet understand, or they formed much more recently than other planets, raising new questions about how quickly planetary systems can change over time. If superpuffs do have a mechanism that allows them to retain their atmospheres despite their low gravity, it could point to entirely new atmospheric dynamics at play. One possibility is that these planets have magnetic fields far stronger than we expect, which could act as a protective barrier against stellar winds and radiation. But this raises another issue. How would a planet with such a low-density core generate a strong magnetic field? On Earth, Jupiter, and other magnetic planets, it is the movement of molten metals in the core that produces these fields. If superpuffs lack a dense core, what is driving their magnetic activity? Another theory suggests that superpuffs could be cloaked in an extensive ring system, similar to Saturn's, which makes them appear much larger than they actually are. If these rings were composed of highly reflective material, they could interfere with our measurements, making it seem as though the planet's radius is larger than it really is. However, this hypothesis has its own set of problems. For one, the ring systems would have to be stable for billions of years, which is unlikely unless they are being actively replenished by some unknown process. Furthermore, planetary rings are usually found around gas giants, not around low-mass planets like the ones classified as superpuffs. The question of their internal composition is another major mystery. If these planets truly are as light and airy as their measurements suggest, then their interiors must be vastly different from anything found in our solar system. Perhaps they contain vast reservoirs of trapped gas, held in place by unusual geological formations that we don't yet understand. Some researchers have even proposed that superpuffs could be composed of exotic forms of ice or other materials that expand under certain conditions, keeping them inflated. Recent observations have also suggested that the atmospheres of some superpuffs contain large amounts of water vapor, which complicates things even further. Water is a relatively heavy molecule compared to hydrogen and helium, which means that if these planets were made primarily of water vapor, their densities should be higher, not lower. This raises the possibility that superpuffs might have unusual atmospheric layering, with different gases distributed in ways we haven't seen before. There's also the possibility that superpuffs are simply a temporary phase in planetary evolution. Perhaps they start out as inflated, low-density worlds but gradually shrink over time as they lose their atmospheres. If this is the case, then we might be catching these planets at a very specific moment in their lifespan, making them even rarer than we thought. This would mean that for every superpuff we see, there may have been countless others that have already transitioned into more compact worlds, leaving little trace of their former state. One of the biggest hurdles in studying superpuffs is that they are difficult to observe in detail. Most of the ones we know about are located hundreds of light years away, making it hard to gather precise data about their atmospheres and compositions. However, advancements in telescopes and observational techniques are gradually allowing us to probe deeper. The James Webb Space Telescope, for example, has the capability to analyze their atmospheres with unprecedented precision, potentially revealing new clues about their structure and origin. If JWST and future telescopes confirm that superpuffs have compositions or atmospheric dynamics that defy conventional models, it could revolutionize our understanding of exoplanet science. We might need to rethink not just how planets form, but also the fundamental physics that govern their atmospheres and internal structures. Could there be unknown physical forces at work? Could these planets represent an entirely new category of celestial objects that we have yet to classify properly? As we continue our search for habitable worlds beyond our solar system, understanding superpuffs could be crucial. If they turn out to have exotic chemical compositions, they might reveal new pathways for planetary habitability that we never considered. Could a superpuff host life in its dense, cloud-filled atmosphere? Could its unusual properties make it an ideal candidate for supporting microbial organisms, similar to what has been proposed for the upper clouds of Venus? The deeper we dive into the mystery of superpuffs, the more questions arise. These planets refuse to fit neatly into existing categories, defying expectations at every turn. They are a stark reminder that, despite all of our advancements in astrophysics, we are still just scratching the surface when it comes to understanding the vast diversity of worlds in the universe. The mystery of superpuffs isn't just about their size or density, it's about what they represent in the grander scheme of planetary science. Every new discovery about them challenges what we thought we knew about how planets form, evolve, and survive in extreme conditions. These worlds, with their seemingly impossible characteristics, could be the key to unlocking secrets about planetary diversity across the universe. One of the most puzzling aspects of superpuffs is their apparent resistance to atmospheric loss. Typically, planets with low gravity and close orbits around their stars should be stripped of their atmospheres over time. Stellar winds and radiation exert immense pressure on planetary atmospheres, causing them to evaporate into space. Yet, superpuffs remain inflated, holding on to their gas layers in defiance of this expectation. Scientists have theorized that these planets might possess unique atmospheric compositions that make them more resistant to loss. For example, a thick, hazy layer of aerosols or high-altitude clouds could protect the lower atmosphere from direct exposure to stellar radiation. This would act like a planetary shield, slowing down the rate of atmospheric escape. Another hypothesis suggests that these planets are somehow replenishing their atmospheres faster than they lose them. If superpuffs have active geological or chemical processes that continuously release gases from their interiors, they could maintain their fluffy compositions for much longer than expected. This would require a process unlike anything seen in our solar system. On Earth, volcanic activity releases gases like carbon dioxide and water vapor, contributing to the atmosphere, but this occurs on a rocky world with a solid crust. For a gas-dominated planet like a superpuff to achieve a similar effect, it would need a source of internal heating or chemical interactions that are not yet fully understood. Some researchers have proposed that superpuffs could be remnants of failed gas giants, planets that started forming as large gas worlds but were somehow stunted in their development. If their formation was interrupted before they could accumulate enough mass to compress into denser planets, they might have ended up stuck in this puffy, low-density state. This could mean that superpuffs are more common in the universe than we currently realize, but many of them may have already evolved into denser worlds, leaving only a few examples behind for us to observe. There is also the possibility that superpuffs are not as uniform as they appear. When we measure an exoplanet's density, we are making an assumption based on its observed size and mass. But what if these planets have complex internal structures that skew those measurements? Some models suggest that superpuffs could have thick outer layers of hydrogen and helium, with much denser cores than expected. This could create the illusion of an extremely low-density world when, in reality, they are more like gas dwarfs with unusually extended atmospheres. If this is the case, then the challenge lies in determining the actual mass distribution within these planets, something that current observational methods struggle to do with precision. Another fascinating possibility is that superpuffs could have compositions that are radically different from what we assume. In our solar system, planets are mostly composed of rock, metal, gas, and ice, but what if superpuffs contain significant amounts of other exotic materials? Some scientists have speculated that these planets could harbor large amounts of supercritical fluids, substances that exist in a state between gas and liquid under extreme pressure. If the interiors of superpuffs contain vast reservoirs of supercritical hydrogen or helium, it could explain why they appear so inflated while still being able to retain a stable structure. Looking deeper into their atmospheres might also provide clues about their origins. Spectroscopic analysis has already revealed hints of water vapor in some superpuffs, but what if they contain other unexpected elements? If their atmospheres are rich in carbon-based molecules or unusual chemical reactions, it could indicate that they formed in environments vastly different from traditional planetary formation models. This could mean that superpuffs are the remnants of disrupted planetary migration, having formed in colder regions of their star systems before drifting closer to their stars. The existence of superpuffs also raises questions about how common extreme exoplanets might be. If these planets exist in multiple star systems, then what other strange, previously unimagined worlds are out there? Are there even larger superpuffs that defy density expectations even further? Could there be inverse planets, worlds that are significantly denser than expected for their size, existing as compact, solid spheres unlike anything in our solar system? The discovery of superpuffs has expanded our understanding of what planets can be, proving that the universe is far more varied and unpredictable than we ever anticipated. With upcoming technological advancements in telescope capabilities, we may soon uncover even more details about these strange, fluffy worlds. The James Webb Space Telescope, for instance, has already begun probing exoplanet atmospheres with unprecedented precision. If it can gather more data on the molecular makeup of superpuffs, we might finally begin piecing together the truth behind their existence. Future missions, such as next-generation space telescopes with even greater sensitivity, could allow us to directly image these planets in more detail, revealing their cloud structures, atmospheric layering, and even possible weather patterns. Imagine if we were able to see a superpuff up close. What would its skies look like? Would it have swirling, pastel-colored clouds covering its entire surface? Would its atmosphere be thick enough to create a perpetual haze, obscuring any potential ground beneath? Could it have massive storm systems, similar to Jupiter's Great Red Spot, but on an even more extreme scale due to its unique composition? The possibility of observing such an alien world in detail is one of the most exciting prospects in exoplanetary research. As we push the boundaries of what we know about planets, superpuffs serve as a reminder that the universe does not conform to our expectations. They challenge us to think beyond conventional models and explore new possibilities that we may have overlooked. Perhaps the strangest part of all is that superpuffs might not even be the weirdest planets out there. If we've already discovered worlds that defy known physics, what else is lurking in the cosmos, waiting to be found? The search for answers about superpuffs is not just a quest for understanding these particular planets. It's a window into the broader mysteries of planetary formation, evolution, and the sheer diversity of worlds that exist in the universe. Every time we uncover something unexpected, like these ultra-low-density planets, it forces scientists to rethink long-standing theories about how planets grow and change over time. One of the biggest challenges in understanding superpuffs is that we can only study them indirectly. Unlike planets in our own solar system, where we can send probes and analyze samples, exoplanets are detected and studied through distant observations. Most of what we know comes from transit observations, where a planet passes in front of its star, blocking some of the light. This tells us the planet's size. Then, radial velocity measurements help determine its mass by analyzing how much the planet's gravity pulls on the star. But these methods rely on a lot of assumptions. And when those assumptions are wrong, we get surprising results, like planets that seem far too fluffy to exist. There's also the question of whether superpuffs are a short-lived phase in a planet's evolution. If they are, it could mean that they don't last long before transforming into something else. One idea is that they might be young planets that haven't fully settled yet. In the early stages of planetary formation, a newly formed world is often much larger due to leftover heat and the expansion of its atmosphere. Over time, as it cools, it contracts into a denser form. If superpuffs are just young planets in the middle of this process, then what we're seeing might not be an entirely new type of world but rather a brief stage that all planets go through before stabilizing. But this theory has problems. Some of the superpuffs we've detected are orbiting old stars, meaning they should have had plenty of time to shrink if they were going to. Yet they remain puffy, which suggests they have some mechanism keeping them inflated. This brings us back to the possibility that they have thick, extended atmospheres that are somehow resisting collapse. One reason this could happen is if their atmospheres contain large amounts of molecular hydrogen, which is extremely light and allows gas to spread out more. If superpuffs are rich in hydrogen, it might explain why their densities are so low, because much of their volume is made up of lightweight gas that doesn't compress easily. But even that explanation doesn't fully solve the mystery. If their atmospheres are so extended, why haven't they been stripped away by their stars? Many superpuffs are relatively close to their stars, where solar radiation is intense. Normally, planets in these positions experience atmospheric loss as the high-energy radiation blasts away their outer layers. So why do superpuffs seem immune to this? One possibility is that they are protected by powerful magnetic fields. On Earth, our magnetic field helps shield us from solar wind, preventing our atmosphere from being stripped away. If superpuffs have strong magnetic fields, they could be deflecting much of the radiation that would otherwise erode their atmospheres. However, this would require a highly active core generating such a field, which raises further questions about what's inside these planets. If they have thick, gaseous envelopes but still have active cores, their internal structures must be very different from anything we've seen before. There's also the idea that superpuffs are actually covered in layers of high-altitude clouds or hazes that make them appear larger than they really are. If we're measuring their radii based on the outermost visible layer of their atmosphere, but that layer is mostly made up of suspended particles or aerosols, then their actual size could be smaller than it appears. This would mean their densities aren't quite as extreme as we think, but it still wouldn't fully explain why they maintain such thick atmospheres. The question of their origins is just as puzzling as their structure. Did superpuffs form in place, or did they migrate from other regions of their solar systems? Many exoplanets are thought to have moved from where they originally formed due to gravitational interactions with other planets, or their stars. If superpuffs started in much colder regions, they could have formed with large amounts of volatile gases like hydrogen and helium, which then expanded as they migrated to warmer regions. This could explain their large sizes, but it still doesn't clarify why they haven't lost their atmospheres over time. Another strange possibility is that superpuffs are what's left of larger planets that lost some of their mass. If a gas giant like Jupiter were stripped of much of its outer atmosphere due to some catastrophic event, like a massive collision or extreme solar radiation, it could leave behind a puffy remnant that looks like a superpuff. This idea is intriguing because it suggests that superpuffs might not be a unique type of planet at all, but rather the broken remains of larger worlds that have been reshaped by cosmic forces. Regardless of their origins, studying superpuffs gives us insight into the vast range of planetary types that exist beyond our solar system. The more we learn about them, the more we realize that planetary formation is not a simple, one-size-fits-all process. There may be many different ways for planets to form and evolve, and some of them might result in worlds that defy our expectations. Future missions and telescopes will help us get closer to answering these questions. The James Webb Space Telescope is already providing more detailed data on exoplanet atmospheres than ever before, and upcoming projects like the Extremely Large Telescope, ELT, will push our observational capabilities even further. With these tools, we might finally be able to analyze the chemical compositions of superpuffs in greater detail, revealing whether their atmospheres contain exotic elements, unexpected molecular structures, or even signs of complex weather patterns. There's also the exciting possibility that superpuffs could have moons or rings that we haven't detected yet. If some of these planets are surrounded by thin rings, it could slightly alter their measured sizes, making them appear larger and fluffier than they actually are. Similarly, if they have large, close-orbiting moons, gravitational interactions could play a role in keeping their atmospheres inflated in ways we don't yet understand. Ultimately, the mystery of superpuffs reminds us how little we know about the universe. Every time we think we have a solid grasp on planetary science, something like this comes along and forces us to reconsider everything. These ultra-low-density exoplanets could be telling us something fundamental about how planets form and evolve, something that we haven't even begun to understand yet. And if superpuffs can exist, what other strange planets are waiting to be discovered? Could there be even more extreme versions, planets with densities so low they're on the edge of stability? Could there be the opposite, planets so dense that they break our understanding of how matter behaves on a planetary scale? The deeper we look into space, the more we realize that the universe is full of surprises, and superpuffs are just one of many mysteries waiting to be unraveled. The deeper we dive into the mystery of superpuffs, the more we realize that they challenge the very core of planetary science. If these planets exist as they appear, massive, low-density worlds with atmospheres extending far beyond what we thought possible, then they are rewriting the rules of how planets can form and survive. The idea that a planet can be this large and yet so lightweight seems almost paradoxical. It's like discovering a basketball the size of a house but weighing as much as a loaf of bread. How is that even possible? One of the most mind-boggling aspects of superpuffs is their extreme difference from the planets in our own solar system. Even the gas giants in our neighborhood, Jupiter, Saturn, Uranus, and Neptune, are significantly denser. This makes sense because, as a planet accumulates mass, gravity should compress it further, making it denser. But superpuffs defy that logic. They have a mass similar to Neptune's but an enormous radius, making them far less dense than expected. Scientists are still searching for an explanation that accounts for their bizarre physical properties. One of the leading theories for their strange characteristics is that they have atmospheres dominated by incredibly light gases, such as hydrogen and helium. But even this raises more questions than it answers. If their atmospheres are so expanded and tenuous, why haven't they been stripped away by their parent stars? Many superpuffs orbit close to their stars, meaning they are constantly bombarded by stellar radiation and solar winds. Normally, this would cause atmospheric escape, gradually eroding the planet's outer layers over time. Yet, despite this, superpuffs remain inflated and low density. What is keeping their atmospheres from dissipating into space? One possibility is that these planets formed much farther from their stars, where conditions were colder and allowed them to accumulate large amounts of gas. Then, at some point in their history, they migrated inward due to gravitational interactions with other planets, or their host star. This means they could have originally formed in a much more distant, icy region, accumulating thick atmospheres before slowly drifting closer to their stars. However, if this were the case, we would expect them to have lost much of their atmospheres by now due to the intense radiation at their new locations. The fact that they haven't suggests there is something unique about their atmospheric composition or internal structure that we don't yet understand. Another fascinating idea is that superpuffs might not be as fluffy as they seem. Instead, they could be shrouded in thick layers of clouds or high-altitude hazes that distort our measurements. If a planet's atmosphere is filled with dense clouds, it can create the illusion that the planet is larger than it really is. This means that our current calculations might be overestimating their size, making them appear more inflated than they actually are. However, even if this were the case, it wouldn't fully explain why these planets seem to have such low densities. Their mass measurements, which are based on how much they tug on their parent stars, still suggest that they are unusually light for their size. There's also a more exotic possibility. What if superpuffs aren't normal planets at all? What if they are something entirely different, an entirely new class of celestial objects that don't fit neatly into our current understanding of planets, moons, or gas giants? Some researchers have speculated that they could be failed stars, objects that began forming like stars but never accumulated enough mass to ignite nuclear fusion. Others have suggested that they could be the remnants of disrupted gas giants, planets that once had much larger masses but lost most of their material due to extreme cosmic events. Yet another theory suggests that superpuffs might contain large amounts of hidden mass in a way that we don't yet fully understand. Could they have massive, dense cores buried deep within their atmospheres, surrounded by thick layers of gas that make them appear more inflated than they really are? If so, then our measurements might be misleading us about their true nature. Some scientists have even considered the possibility that superpuffs could be harboring vast ring systems that are skewing our observations. If a planet has massive rings, those rings could reflect light and make the planet appear much larger than it actually is. We've seen this happen in our own solar system with Saturn, which looks significantly bigger when its rings are included in measurements. Could superpuffs have rings so large that they are distorting our measurements of their radii? The presence of rings could also help explain why these planets seem to retain their atmospheres despite being close to their stars. If the rings are made of ice and dust, they could act as a protective barrier, shielding the planet's atmosphere from stellar radiation. This would allow them to maintain their puffy, low-density structures for far longer than we would otherwise expect. However, detecting such rings around distant exoplanets is incredibly difficult, and as of now, there's no direct evidence to support this idea. Perhaps the most exciting possibility is that superpuffs could be key to discovering entirely new physics. If their densities are truly as low as we think, then they might be defying some of our fundamental assumptions about how planets form and evolve. Could they be made of exotic materials that we don't yet understand? Could they contain hidden elements or chemical compounds that interact with gravity and atmospheric pressure in ways we haven't encountered before? The discovery of superpuffs has already pushed scientists to rethink their models of planetary formation. Traditional theories suggest that planets should form in a way that leads to relatively predictable densities, with gas giants being denser than ice giants and rocky planets being denser than both. But superpuffs completely break this pattern. Their existence suggests that there may be many more exotic types of planets out there, waiting to be discovered, some that might be even stranger than what we've seen so far. Upcoming telescopes and space missions will play a crucial role in uncovering the truth about these baffling worlds. The James Webb Space Telescope, for example, is already providing unprecedented levels of detail about exoplanet atmospheres, allowing scientists to analyze the chemical compositions of distant worlds like never before. If Webb can get a closer look at the atmospheres of superpuffs, it might help determine whether their strange properties are due to thick clouds, unusual gases, or something even more mysterious. Additionally, new space telescopes like the European Space Agency's Ariel mission, which is set to launch in the coming years, will be specifically designed to study exoplanet atmospheres in detail. With these powerful tools, scientists may finally be able to unravel the true nature of superpuffs and determine whether they are simply an anomaly or if they represent an entirely new category of celestial objects. Regardless of what the future holds, one thing is certain: superpuffs are a reminder that the universe is far more complex and fascinating than we ever imagined. Just when we think we have a solid understanding of how planets work, nature surprises us with something completely unexpected. These ultra-low-density worlds challenge everything we know about planetary science and force us to consider possibilities that once seemed impossible. And if superpuffs exist, what else is out there? Could there be planets even stranger than these? Worlds with atmospheres made of exotic, unknown substances? Planets that completely defy the laws of physics as we understand them? The search for answers is just beginning, and every new discovery brings us one step closer to understanding the true nature of the cosmos. The existence of superpuffs is just the beginning of what could be an even larger mystery. If these planets truly defy traditional models of planetary formation, then they may not be isolated cases. Instead, they could be the first signs that our understanding of planetary evolution is incomplete, or even fundamentally flawed. If we've already found a handful of these bizarre, ultralight worlds, how many more are lurking out there in the vast expanse of the universe? Could they be common, or are they rare, freak occurrences? And if they're common, how have we not discovered them sooner? One possibility is that superpuffs are actually a transitional phase in a planet's evolution. What if we are catching them at a unique moment in their lifespan, a stage where their atmospheres are still inflated before eventually collapsing into a denser state? This would mean that superpuffs aren't a distinct type of planet but rather a temporary phase that many planets go through. If this is true, then our understanding of planetary life cycles could be entirely wrong. We might have to rewrite our theories about how gas giants and other large planets evolve over time. But if superpuffs are a temporary phase, then what causes them to transition out of it? Is it a slow process, taking billions of years, or can it happen suddenly due to a major cosmic event? If we could observe a superpuff in the process of changing, we might be able to answer this question. However, given the vast timescales involved in planetary evolution, witnessing such a transformation in real time might be nearly impossible. The only way to know for sure would be to study as many superpuffs as possible and look for patterns, something that current and future telescopes may help us accomplish. Another mind-bending theory is that superpuffs could be remnants of ancient planetary collisions. Imagine a massive gas giant, like Jupiter, being struck by an enormous object, perhaps another planet, a rogue moon, or even a failed star. The impact could have stripped away much of the planet's original mass, leaving behind only a diffuse, puffy remnant. This would explain why superpuffs have such low densities despite their large sizes. They could be the cosmic leftovers of planetary destruction, the ghosts of once massive worlds that were torn apart by catastrophic events. If this were the case, then studying superpuffs could provide insight into the violent history of planetary systems. We know that planetary collisions were common in the early days of our own solar system. Earth itself is thought to have been struck by a Mars-sized object, which likely led to the formation of the Moon. Could superpuffs be evidence that such massive impacts are even more common in the universe than we realized? If so, then these planets could serve as natural laboratories for studying the aftermath of planetary collisions. But there's another, even stranger possibility. What if superpuffs aren't planets at all? What if there's something entirely new, something that doesn't fit into our existing categories of celestial objects. Some scientists have speculated that they could be failed stars, objects that tried to ignite nuclear fusion but never gathered enough mass to succeed. If that's the case, then superpuffs might be more similar to brown dwarfs, star-like objects that never quite became full-fledged stars, than to traditional planets. Alternatively, superpuffs could be artificial in nature. This might sound like pure science fiction, but consider this. If an advanced alien civilization wanted to build massive structures in space, they would need enormous amounts of material. What if superpuffs are actually the remains of giant space megastructures, slowly decaying over time? This is an extremely speculative idea, but it's not entirely impossible. After all, if we stumbled upon an artificial object the size of Jupiter but with the density of cotton candy, how would we distinguish it from a naturally occurring planet? Of course, there's no concrete evidence to suggest that superpuffs are artificial, but the fact that they defy conventional explanations makes it a possibility worth considering. If they were artificial, we would expect to find unusual chemical compositions, strange heat signatures, or even signs of structural patterns in their atmospheres. Future telescopes might be able to analyze their chemical makeup in more detail, potentially revealing clues that could settle the debate once and for all. Regardless of their origin, the mere existence of superpuffs forces us to question what we think we know about the universe. These planets break the rules, challenge our theories, and demand answers. But perhaps the most exciting thing about them is what they represent: the idea that the universe is still full of surprises. For centuries, we have tried to classify and categorize celestial objects, putting them into neat boxes that align with our scientific models. But superpuffs refuse to be categorized. They exist in a space between planets and gas giants, between what we understand and what we don't. And if superpuffs are this strange, what other mysteries are waiting to be discovered? Could there be planets made entirely of liquid? Worlds with atmospheres thicker than stars? Planets that orbit black holes in ways we never imagined? The more we explore, the more we realize that the universe is far more complex and bizarre than we ever expected. As we continue to study superpuffs, we may not only unlock the secrets of these strange worlds, but also gain a deeper understanding of how planets form, how they evolve, and what kinds of exotic objects may be hiding in the cosmos. And with each new discovery, we take another step toward answering the biggest question of all: what else is out there, waiting to be found? Superpuffs are just one piece of the cosmic puzzle, but their existence suggests that the universe has many more surprises in store. These ultralight, oversized planets raise questions that go beyond planetary science and reach into the very nature of how matter behaves under extreme conditions. If superpuffs can exist, then what else might be possible? Could there be planets with densities even lower than we've seen so far? What if there are planets so diffuse that they barely qualify as solid bodies at all? One of the biggest challenges in studying superpuffs is their distance from Earth. Most of them have been discovered through the transit method, where telescopes detect dips in a star's brightness as a planet passes in front of it. This method is excellent for identifying planets, but it doesn't tell us much about their composition. To truly understand what these planets are made of, we need more detailed observations. Future space telescopes, such as the James Webb Space Telescope and other next-generation observatories, could provide much-needed data. By analyzing the light that passes through a superpuff's atmosphere, we can determine its chemical makeup. If these planets are primarily hydrogen and helium, that would support the idea that they are simply very inflated gas planets. But if we find unexpected elements, such as high concentrations of water vapor, carbon dioxide, or exotic compounds, it could suggest that superpuffs are something entirely new. One possibility is that superpuffs have incredibly thick cloud layers that make them appear larger than they really are. If their atmospheres contain high-altitude hazes, this could give them a puffy appearance without requiring them to be truly low-density. Some scientists believe that hazy atmospheres could explain at least some of the observed properties of these planets. However, this doesn't fully resolve the mystery, because even if we account for thick clouds, their densities are still much lower than expected. Another strange thing about superpuffs is their relationship to their host stars. Many of the known superpuffs orbit relatively close to their stars, meaning they are exposed to intense radiation. Normally, this kind of radiation would strip away a planet's atmosphere over time, but somehow, superpuffs have managed to retain their enormous, fluffy atmospheres. This suggests that either they are very young planets that haven't had time to lose their atmospheres yet, or they have some unknown mechanism keeping them inflated. Could superpuffs have powerful magnetic fields that help shield their atmospheres from stellar radiation? If so, that would be a groundbreaking discovery, because it would mean that even lightweight planets can generate strong magnetic fields, something we previously thought was limited to more massive planets like Earth or Jupiter. Alternatively, superpuffs might be constantly replenishing their atmospheres from internal sources, perhaps through volcanic activity or other processes we don't yet understand. Some astronomers have even suggested that superpuffs might not be planets at all, but instead, they could be massive, slow-rotating dust clouds that only appear planet-like when viewed from a distance. If this were the case, it would completely change how we interpret exoplanet data. It's possible that what we're seeing as planets are actually temporary structures, giant clouds of gas and dust that are still in the process of forming into real planets. But perhaps the most mind-blowing idea is that superpuffs could be examples of exotic physics at work. What if they contain unknown forms of matter that make them behave differently from normal planets? Could they have strange quantum effects that allow them to remain inflated without collapsing under their own gravity? Some theories suggest that dark matter could play a role in planetary formation, and if that's true, then superpuffs might be the first direct evidence of dark matter interacting with normal matter on a planetary scale. If superpuffs do contain dark matter, then studying them could provide a window into one of the biggest mysteries in physics. Dark matter is thought to make up most of the mass in the universe, yet we've never directly observed it. If superpuffs somehow trap or interact with dark matter, they could become a testing ground for new physics. This would be one of the biggest discoveries in the history of science, completely reshaping our understanding of the cosmos. But even if dark matter isn't involved, the mere fact that superpuffs exist tells us that planetary science is far from settled. Every time we think we have the universe figured out, something like this comes along and forces us to rethink everything. That's what makes space so fascinating. It's full of surprises, and we're only just beginning to uncover them. Superpuffs challenge our understanding of planetary formation in ways that scientists are still struggling to explain. Their existence suggests that our models of how planets form and evolve might be incomplete, or even fundamentally flawed. Theories that once seemed solid now face serious questions. Could superpuffs be an overlooked but common stage in planetary evolution? Or are they a rare anomaly, a cosmic glitch that defies explanation? One of the most puzzling aspects of superpuffs is their sheer size compared to their mass. A planet as large as Jupiter but with the density of cotton candy seems almost impossible. Gravity should pull their atmospheres inward, making them denser. And yet, somehow, they remain puffed up. This raises the question, what force is counteracting gravity and preventing these planets from collapsing into more compact forms? Some scientists suggest that extreme internal heating might be the answer. If a superpuff has an unusually hot core, it could be driving strong convection currents within its atmosphere. This could create a sort of heat balloon effect, where internal pressure keeps the atmosphere expanded beyond what we would expect. However, if this were the case, we would expect superpuffs to emit more infrared radiation than they do. Their relatively low temperatures suggest that internal heat alone cannot fully explain their puffy nature. Another possible explanation is that these planets are still very young. If a superpuff recently formed, it might still be in the process of cooling and contracting. In this case, we may be observing them at a temporary stage of their evolution. Over millions or billions of years, they could shrink down into denser planets, and we just happen to be catching them in a brief moment of their planetary life cycle. But this raises another problem. If superpuffs are just a temporary phase, why have we found multiple examples of them? Shouldn't they be extremely rare? Some scientists believe that these planets might have formed in a unique way, very different from the gas giants in our own solar system. Most large planets form by first accumulating a solid core and then attracting large amounts of gas. But what if superpuffs formed in a gas-rich environment where their atmospheres were able to grow much larger before they ever developed a dense core? If this were the case, it would suggest that superpuffs are relics of a very different planetary formation process, one that might have been much more common in the early universe. The presence of thick cloud layers could also be playing a role in making these planets appear larger than they really are. Some researchers suggest that if superpuffs have highly reflective, high-altitude clouds, they might be scattering light in a way that makes their atmospheres seem more extended than they actually are. However, even if we account for this, their densities are still lower than any known planets, meaning that cloud layers alone cannot be the full explanation. Another possibility is that superpuffs contain a large amount of water vapor in their atmospheres. Water has a lower molecular weight than the hydrogen and helium that make up most gas giants, which means a water-rich atmosphere would naturally be less dense. If these planets formed in regions of space rich in ice and water, they might have developed in a way that makes them fundamentally different from the planets we see in our own solar system. But perhaps the most radical explanation is that superpuffs aren't planets at all, at least not in the way we think of them. What if they are actually failed stars, objects that formed with just barely too little mass to trigger nuclear fusion? In this case, they might be more similar to brown dwarfs than to traditional planets. If true, it would mean that superpuffs belong in an entirely new category of celestial objects, one that doesn't fit neatly into our current definitions of planets or stars. Another mind-blowing idea is that superpuffs could be evidence of unknown physics at play. Some theorists have suggested that these planets might be filled with exotic forms of matter that behave differently than the normal atoms and molecules we're familiar with. Could they be composed of an unknown substance that naturally resists compression? If so, studying them could give us insight into new branches of physics that we have yet to discover. If there's one thing we know for sure, it's that the discovery of superpuffs has raised more questions than answers. And with each new exoplanet discovery, the universe only gets stranger. Could there be even puffier planets out there, ones with densities lower than anything we've ever imagined? Could there be planets made almost entirely of gas, with barely any solid core at all? The more we search, the more we realize that we've only scratched the surface of what's possible in the cosmos. The more we learn about superpuffs, the more baffling they become. These planets break almost every rule we thought we understood about planetary formation, composition, and structure. If they are just gas giants with incredibly inflated atmospheres, then why haven't we seen anything like them in our own solar system? If they are a temporary phase of planetary evolution, why do we keep finding multiple examples of them across different star systems? And if they are something entirely different, then what could they possibly be? One of the strangest aspects of superpuffs is their survival. Given their extremely low density, one would expect these planets to be vulnerable to atmospheric loss, especially if they orbit close to their stars. Intense stellar radiation should gradually strip away their atmospheres, causing them to shrink over time. And yet, despite their delicate nature, they seem to persist. This suggests that there may be some unknown mechanism protecting their atmospheres, preventing them from dissipating as quickly as expected. Some scientists have proposed that these planets could have magnetic fields far stronger than what we would normally expect for planets of their size and mass. A strong magnetic field could act as a protective shield, deflecting charged particles from the host star and preventing atmospheric erosion. But the problem with this theory is that generating a strong magnetic field typically requires a fast-spinning, metallic core, something that these light, fluffy planets may not even have. If superpuffs really do have powerful magnetic fields, it could mean that there is a whole new mechanism for planetary magnetism that we have yet to discover. Another theory is that these planets are continuously replenishing their atmospheres. If they have active geological or atmospheric processes that release large amounts of gas over time, it might help counteract the effects of atmospheric loss. Volcanic activity, deep-seated outgassing, or even large-scale chemical reactions within their atmospheres could be producing fresh gas at a rate that keeps up with the rate of atmospheric escape. However, for this to be true, superpuffs would need to be geologically active in a way that no other known planet is. The possibility that superpuffs contain vast amounts of water vapor is also intriguing. If these planets are primarily made of water rather than hydrogen and helium, they would naturally be less dense. But this raises another question: how did they form in environments with so much water? Did they originate in the outer regions of their star systems, where ice is more abundant, and then migrate inward? Or did they form in an entirely different way from the gas giants we're familiar with? Some astronomers have speculated that superpuffs could be the remnants of planetary collisions. If a gas giant were struck by a massive impactor, it could potentially lose much of its rocky core while retaining its atmosphere. The result could be a planet with an extremely low density, essentially a gas giant that has been hollowed out by a cataclysmic event. However, for this to explain all the superpuffs we've found, such collisions would have to be relatively common, which seems unlikely. But perhaps the most mind-bending possibility is that superpuffs represent an entirely new category of objects that don't fit neatly into our current understanding of planets. Some researchers have suggested that they could be made of exotic forms of matter that resist compression in ways we don't yet understand. If they contain unknown subatomic particles or interact with dark matter in some way, it could explain why they remain so large despite their low mass. If dark matter plays a role in the structure of superpuffs, studying these planets could provide critical clues about one of the biggest mysteries in physics. Dark matter is believed to make up most of the universe's mass, yet we have never directly detected it. If these planets somehow interact with dark matter differently than other planets, they could serve as a natural laboratory for studying this elusive substance. Another possibility is that superpuffs are not planets at all, but instead are some kind of transient celestial structure, perhaps a loosely bound cloud of dust and gas that only appears planet-like when observed from a distance. If this is the case, it would mean that some of the planets we've detected through the transit method might not actually be solid worlds, but rather temporary accumulations of gas that have yet to fully collapse into stable planetary bodies. Whatever the answer, superpuffs prove that the universe is far stranger than we ever imagined. Every time we think we understand how planets form and evolve, we discover something that forces us to question everything. These mysterious, fluffy worlds remind us that science is never truly settled, and that the cosmos will always hold surprises beyond our wildest expectations. Superpuffs continue to defy logic, and every attempt to explain them leads to even more questions. If they are just extremely inflated gas giants, what stops their atmospheres from collapsing under their own weight? If they are a young stage of planetary evolution, why do we see so many of them in different star systems instead of just a handful? And if they are something completely different, what could they possibly be? One of the most striking problems is that they shouldn't even exist in stable orbits. Given their low mass and enormous size, their gravitational hold on their own atmospheres is weak. This means that the intense radiation from their host stars should be gradually stripping away their gas layers. Over time, they should shrink into denser, more compact planets. But instead of seeing superpuffs in the process of losing their atmospheres, we find them fully intact, seemingly defying physics. This leads some astronomers to suspect that superpuffs might have extremely strong atmospheric winds that redistribute heat and gas in a way that prevents atmospheric loss. If winds move quickly enough across the planet's surface, they could spread heat and energy evenly, reducing localized heating from the star and preventing gas from escaping. However, for this to work, these planets would need wind speeds far beyond anything we've observed before. Jupiter's Great Red Spot, a storm that has raged for centuries, moves at around 430 to 680 kilometers per hour. But the winds on a superpuff would need to be orders of magnitude faster, possibly reaching thousands of kilometers per hour, to create the necessary stabilizing effect. Another possibility is that these planets have some unknown internal energy source that replenishes their atmospheres from within. If they have active geological processes that release large amounts of gas into their atmospheres, this could counteract the effects of stellar radiation. However, this would require a mechanism unlike anything seen in our solar system. Earth's volcanoes release gases, but not on a scale large enough to maintain a planet's entire atmosphere. For superpuffs, this process would have to be continuous and powerful, as if the planet itself were constantly exhaling. Could it be that superpuffs are actually hollow? If their interiors are not as dense as we assume, they might contain vast empty spaces filled with lightweight gases. Instead of being true planets, they could be more like planetary scale balloons, with thick outer shells of gas but little mass on the inside. If this were the case, their densities would make more sense. But it would also mean that they are unlike any other known celestial object. One of the biggest clues about superpuffs might come from their formation history. If they formed farther from their stars in colder regions of space, they might have started out as ice-rich planets before migrating inward. In such a scenario, they could have captured large amounts of gas in their early years, forming thick atmospheres. As they moved closer to their stars, the ice could have sublimated, leaving behind an extremely puffy world made mostly of gas. This would mean that superpuffs are essentially the failed cores of gas giants, planets that never gathered enough mass to become full-fledged giants like Jupiter or Saturn. But what if they didn't form like normal planets at all? Some researchers have suggested that superpuffs might be remnants of disrupted stars, small stellar objects that failed to ignite nuclear fusion and instead cooled into strange, oversized planetary bodies. If this were true, they would be more like rogue brown dwarfs than traditional planets. In this scenario, their low densities might be explained by leftover heat from their formation keeping their atmospheres expanded. However, this raises even more questions. Why do they appear in planetary systems rather than floating alone in space like other failed stars? Did they form alongside their host stars, or were they captured from interstellar space? Another wild possibility is that superpuffs could be partially made of dark matter. If dark matter somehow interacts with normal matter within these planets, it could provide an internal energy source that prevents them from collapsing into denser forms. Dark matter is thought to make up most of the universe's mass, yet we cannot directly detect it. If superpuffs interact with dark matter in a unique way, they could hold the key to unlocking one of the biggest mysteries in physics. The idea that superpuffs might contain exotic forms of matter is also worth considering. There could be unknown chemical processes at play that allow their atmospheres to remain inflated without dissipating. Perhaps their atmospheres contain elements that are extremely rare or even non-existent in our own solar system, giving them physical properties unlike anything we've encountered before. Even more bizarre is the idea that superpuffs might not be natural at all. If an advanced extraterrestrial civilization existed, could they have artificially created these planets? Some theorists have proposed that highly advanced civilizations could manipulate planets on a large scale, using unknown technologies to control atmospheric density and planetary structure. If this were the case, superpuffs could be some kind of alien megastructure, a planetary-scale experiment, or a failed attempt at creating habitable worlds. The biggest challenge in understanding superpuffs is that we have no direct way of studying them up close. Unlike the planets in our solar system, which we can observe in detail with probes and telescopes, exoplanets are detected indirectly. We primarily study them by analyzing how they block the light of their host stars as they pass in front of them. This transit method gives us information about their size and density, but not much else. We don't know what their atmospheres are made of, what their surfaces look like, or whether they have moons or rings. Until we develop better ways to study them, we can only make educated guesses. Despite the many unknowns, one thing is clear: superpuffs are a challenge to our understanding of planetary science. They don't fit neatly into any existing category, and their existence forces us to reconsider everything we thought we knew about how planets form and evolve. Are they failed gas giants? Are they remnants of a completely different formation process? Are they something even stranger? The more we look at the universe, the more we realize how little we truly understand. Every time we discover something new, it shatters our old assumptions and opens up even bigger mysteries. Superpuffs remind us that the cosmos is still full of surprises, and that the strangest discoveries may still be ahead of us. The mystery of superpuffs is far from solved, and every new piece of data seems to raise even more questions. These planets challenge our understanding of planetary formation, composition, and even fundamental physics. Their incredibly low densities suggest that they are unlike any planets we've seen before, and yet, they exist in multiple star systems across the galaxy. If superpuffs are as common as they seem to be, then they must be forming through some process we don't yet fully understand. The challenge is figuring out exactly what that process is. One possibility is that superpuffs formed in environments rich in volatile gases like hydrogen and helium. If a young planet had an unusually high concentration of these light elements, it could grow into an inflated, low-density world. But this explanation only works if the planet remains in a stable environment where it doesn't lose its atmosphere over time. This is one of the biggest contradictions with superpuffs. They are found close enough to their stars that their atmospheres should have been stripped away by radiation and solar winds. But instead they remain intact, floating in space like massive, underinflated balloons. The radiation problem is a huge obstacle for our current understanding. A planet as large and low in density as a superpuff should be highly susceptible to atmospheric loss. In our own solar system, we see this happening all the time. Mars, for example, lost most of its atmosphere over billions of years because it didn't have a strong magnetic field to protect it from solar winds. Even gas giants like Jupiter and Saturn, which have thick atmospheres, are slowly losing mass over time due to interactions with the Sun. But superpuffs, despite their enormous size and weak gravity, somehow manage to keep their atmospheres for millions, possibly billions, of years. One potential explanation is that superpuffs have some form of unknown atmospheric shielding. If their atmospheres contain unusual chemical compounds, they might be more resistant to radiation than we expect. It's possible that superpuffs have thick, high-altitude clouds made of exotic materials that act as a protective barrier, reducing the rate of atmospheric loss. These clouds could also explain why superpuffs appear so puffy. If their upper atmospheres are filled with dense cloud layers, they might scatter light in a way that makes the planet appear larger than it really is. But without direct atmospheric data, this remains pure speculation. Another strange aspect of superpuffs is their potential temperature differences. Because they are so large and diffuse, their interiors might have extremely low temperatures compared to other planets of similar size. If superpuffs have deep, insulating atmospheres, they could trap heat differently than traditional gas giants. This could mean that their interiors are colder than expected, which might explain their unusually low densities. If their core temperatures are too low, they might not have the same level of atmospheric convection that keeps gas giants stable. This could contribute to their bloated appearances, making them even more unusual. A major breakthrough in studying superpuffs would be detecting their atmospheric compositions. If we could analyze the chemical makeup of their atmospheres, we might be able to determine what keeps them inflated. This is where telescopes like the James Webb Space Telescope, JWST, could play a crucial role. JWST is designed to study exoplanet atmospheres in detail by analyzing the way starlight passes through them. If we can determine what gases are present in a superpuff's atmosphere, we might get closer to solving the mystery. But what if superpuffs aren't natural at all? This might sound like a wild idea, but the possibility of artificial planetary structures has been proposed before. Some scientists speculate that extremely advanced civilizations could manipulate planetary atmospheres or even construct artificial worlds. If a civilization had the capability to engineer a planet, it might create a superpuff as a massive structure with an artificial atmosphere. Such a world could serve as a gigantic space station, a planetary-scale habitat, or even an experiment in planetary engineering. While there's no evidence to support this idea, it's worth considering that some of the strangest objects in the universe might have explanations beyond natural planetary formation. If we ever find a superpuff with chemical signatures that don't match natural processes, it could hint at something extraordinary. Until then, however, we have to assume that these planets are natural, no matter how bizarre they seem. Another question that remains unanswered is whether superpuffs could support life. Their low densities and thick atmospheres suggest that they wouldn't have solid surfaces, making them more like gas giants than terrestrial planets. However, that doesn't necessarily rule out the possibility of life. In our own solar system, scientists have proposed that life could exist in the cloud layers of Venus, where temperatures and pressures are more hospitable than on the planet's scorching surface. If superpuffs have stable cloud layers at the right temperatures, it's conceivable that microbial life could exist there, floating in their vast atmospheres. The problem is that we don't know if superpuffs have the right conditions for life. Their chemical compositions remain a mystery, and their atmospheric dynamics are completely unknown. Even if they do have life-supporting elements like carbon, hydrogen, oxygen, and nitrogen, the extreme conditions in their atmospheres might make it impossible for life as we know it to survive. But until we study them in more detail, we can't rule anything out. Superpuffs also raise a more fundamental question. If these planets can exist, what other types of planets might be out there? For most of history, astronomers thought that planetary systems would resemble our own, with rocky planets close to their stars and gas giants farther out. But discoveries like superpuffs have shattered that assumption. If planets with such extreme characteristics exist, there might be even stranger worlds waiting to be discovered. Planets made entirely of water, planets with atmospheres of pure metal vapor, or planets that are nothing but massive, floating gas clouds. One of the best ways to test our theories about superpuffs is to look for more of them. The more superpuffs we find, the better we can understand their distribution, composition, and evolution. If we discover that they are more common around certain types of stars, that might provide clues about how they form. If we find variations in their densities, that could tell us whether they evolve over time or if they represent a stable planetary type. Right now, we are only scratching the surface of what's possible. With new telescopes and better observational techniques, we might finally be able to unlock the secrets of superpuffs. But for now, they remain one of the greatest mysteries of exoplanet science, giant, airy worlds that challenge everything we thought we knew about planets. Superpuffs continue to challenge everything we understand about planetary science, and the more we study them, the stranger they seem to become. They exist in a space that defies our expectations, too large for rocky planets, too diffuse for traditional gas giants, and too stable for something that should be constantly losing its atmosphere. Every explanation we come up with seems to open another door of questions, making them one of the most perplexing types of exoplanets ever discovered. One of the most puzzling aspects of superpuffs is their possible formation process. In traditional planetary formation models, planets emerge from protoplanetary disks of dust and gas surrounding young stars. Rocky planets form when solid material collides and sticks together, while gas giants form when these rocky cores accumulate thick atmospheres of hydrogen and helium. But for a planet to grow as large as a superpuff while remaining so lightweight, something unusual must have happened during its formation. One possibility is that superpuffs started as small rocky cores that somehow captured an extreme amount of gas before the protoplanetary disk dissipated. Normally, gas giants like Jupiter and Saturn are thought to form far from their stars, where hydrogen and helium are more abundant. However, superpuffs are often found much closer to their stars, which raises the question, how did they accumulate so much gas without migrating outward like traditional gas giants? One theory suggests that superpuffs formed in an unusually thick region of their star's protoplanetary disk, where the gas was denser and more readily available. If a planet formed in a gas-rich environment and had weak gravity, it might have absorbed an enormous amount of hydrogen and helium, creating a low-density structure. But even this doesn't fully explain why their atmospheres remain so inflated over time, rather than contracting under gravity. Another theory proposes that superpuffs might have originally formed as ice-rich planets far from their stars and later migrated inward. If these planets contained a large amount of water or other volatile compounds, they could have developed thick atmospheres as they moved closer to their stars. The intense radiation from the star might have caused these ices to vaporize, creating a puffy atmosphere that expanded outward. This could help explain their bloated appearance, but it still doesn't resolve why their atmospheres remain stable over millions of years. One of the biggest mysteries surrounding superpuffs is the possibility that their true nature is even stranger than we imagine. What if these planets aren't simply gas-rich worlds, but something entirely different, something that challenges our very definition of what a planet is? Some scientists have speculated that superpuffs might not be planets in the traditional sense at all, but instead represent a new category of celestial objects, unlike anything we've ever seen. For example, One radical idea is that superpuffs might be remnants of failed stars, objects that began forming like stars but never gained enough mass to ignite nuclear fusion. Brown dwarfs, sometimes called failed stars, exist in a gray area between planets and stars, and some have atmospheric properties similar to gas giants. If a brown dwarf-like object somehow retained an extremely low-density atmosphere, it might resemble a superpuff. However, brown dwarfs tend to be much hotter and denser than the superpuffs we've observed, making this explanation unlikely. Another strange possibility is that superpuffs might be partially hollow. While this might sound like science fiction, there are theoretical scenarios where a planet could have an internal structure full of massive voids or layers of low-density material. If a planet had an unusually porous interior, its overall density would be lower than expected, making it appear puffy. However, we don't yet have the technology to directly observe a planet's internal composition, so this idea remains purely speculative. Even more mind-bending is the suggestion that superpuffs could be artificial in origin. If an advanced alien civilization wanted to construct a massive space habitat, it might create a structure with an extremely low-density atmosphere for insulation or protection. Some theorists have even proposed that Dyson-like structures, mega-scale artificial constructs designed to harness energy from a star, could appear similar to superpuffs if they were surrounded by thick layers of gas. While there is no direct evidence for this, the idea that some superpuffs could be engineered objects is an intriguing one that astronomers cannot completely rule out. The best way to unravel the mystery of superpuffs is to study their atmospheres in detail. If we can determine what elements make up their thick clouds, we might be able to figure out why they remain so bloated. Future telescopes, like the James Webb Space Telescope, JWST, are expected to play a crucial role in this research. By analyzing the way light passes through a superpuff's atmosphere, JWST can identify the chemical signatures of different gases, helping us determine if these planets are composed of hydrogen, helium, water vapor, or something entirely unexpected. Another approach is to look for more superpuffs in different star systems. Right now, we only know of a handful of these strange worlds, but there could be many more waiting to be discovered. If we find superpuffs around a variety of different stars, we might be able to determine if their formation is linked to specific stellar conditions. If they are more common in young star systems, that might suggest they are temporary objects that shrink over time. If they are found in older systems, that could mean they are stable over billions of years, defying our expectations even further. One of the most frustrating aspects of studying superpuffs is that they don't fit neatly into any category. In planetary science, we like to classify objects based on their size, mass, and composition. But superpuffs break those rules. They are too big to be considered terrestrial planets, too low in density to be typical gas giants, and too stable to be temporary anomalies. They exist in a strange middle ground, and until we get more data, we can only speculate about their true nature. But perhaps the most exciting thing about superpuffs is what they represent for the future of exoplanet research. They remind us that the universe is full of surprises, and that even the most unexpected discoveries can teach us something new about how planets form and evolve. If we can solve the mystery of superpuffs, we might unlock new insights into planetary physics, atmospheric science, and even the potential for exotic forms of life. For now, all we can do is keep searching, keep questioning, and keep pushing the limits of what we think we know. Because if superpuffs have taught us anything, it's that the universe is far stranger than we ever imagined, and that the biggest discoveries might still be waiting just beyond the edge of what we understand. Superpuffs continue to challenge planetary scientists, not only because of their strange, bloated nature but because they defy our basic understanding of how planets should behave. If we look at their density alone, they shouldn't even exist. Their atmospheres should have been stripped away by their host star's radiation. Their gravity should be too weak to hold on to such massive gaseous envelopes, and yet they persist. The question is, how? One major challenge in studying superpuffs is that we currently have no direct way to observe their interiors. Everything we know about them is inferred from their size, mass, and atmospheric properties. If we could send a probe into one, like we've done with Jupiter and Saturn in our own solar system, we might be able to get a clearer picture of what's inside. But since they are light years away, we're left with only indirect methods, like transit spectroscopy, to decipher their secrets. Transit spectroscopy is a powerful tool that allows astronomers to study the atmospheres of exoplanets by analyzing the light from their host stars as it passes through the planet's gaseous envelope. By looking at which wavelengths of light are absorbed, we can determine what chemicals are present. If superpuffs have thick hydrogen-helium atmospheres, we would expect to see strong signatures of these elements. But some studies have shown unexpectedly weak signals, suggesting that their atmospheres might be full of high-altitude hazes or clouds that obscure our view. This leads to another major mystery. What are these clouds made of? On Earth, clouds form from water vapor, but in hotter exoplanet atmospheres, we see clouds made of silicates, metals, and other exotic compounds. If superpuffs have clouds thick enough to block our ability to detect their atmospheres properly, they might contain unknown chemical processes that could reshape our understanding of planetary atmospheres. Another peculiar question is whether superpuffs are a fleeting stage in planetary evolution. Could they be planets that are actively shrinking? If a superpuff is slowly losing its outer layers due to stellar radiation, it might eventually shrink down to become a much denser, more typical planet. This could mean that superpuffs are just a temporary phase in the life cycle of some exoplanets, an evolutionary step that we just happen to be catching in action. If this is the case, then our galaxy might be full of planets that used to be superpuffs but have since condensed into more compact worlds. Alternatively, what if superpuffs are actually young planets that haven't finished forming yet? If they are still in the process of cooling and contracting, their low density might just be a temporary condition. Over millions of years, they could slowly become denser, eventually looking more like Neptune or other gas giants. If this theory is correct, it would mean that we are witnessing a stage of planetary evolution that we have never seen before, a snapshot of a world in transition. But then there's the truly bizarre possibility that superpuffs are not just ordinary planets with weird properties, but rather a sign of something much stranger happening in the universe. Some scientists have speculated that these planets could contain exotic forms of matter or even unknown physical processes that we have yet to understand. If our current models of planetary formation can't explain them, then perhaps our models themselves need to be revised. Some researchers have suggested that superpuffs could contain high amounts of dark matter, an invisible, unknown substance that makes up most of the universe's mass. If dark matter interacts with normal matter in unexpected ways, it might create planets with unusual properties, including extremely low density. While this is highly speculative, it highlights just how little we know about the nature of these objects. Another idea is that superpuffs could be the remnants of massive planetary collisions. If two gas-rich planets collided in the past, the resulting debris cloud could have coalesced into a low-density object, trapping large amounts of gas within its structure. This could explain why they seem so puffy. Perhaps they are not fully settled objects, but chaotic remnants of violent past events. The more we learn about superpuffs, the more questions arise. Could they harbor life? If they have thick, stable atmospheres, they might have the right conditions to support exotic microbial lifeforms, perhaps floating organisms that drift through their gaseous envelopes, similar to the way some scientists speculate about life in the clouds of Venus. However, the extreme conditions of these planets, low gravity, high radiation exposure, and unstable atmospheres, make it unlikely that they would be hospitable in the way Earth is. But that doesn't mean we should rule out the possibility entirely. If life can find a way to survive in extreme environments on Earth, like deep-sea hydrothermal vents or acidic lakes, who's to say that it couldn't adapt to the strange conditions of a superpuff? The search for life is one of the driving forces behind exoplanet research, and if we ever find signs of biological activity in an unexpected place, it could change our entire perspective on what makes a planet habitable. Looking ahead, future space telescopes will provide us with better tools to study superpuffs in detail. The James Webb Space Telescope has already begun observing exoplanet atmospheres with unprecedented precision, and upcoming missions like the European Space Agency's Aerial Telescope will focus specifically on atmospheric characterization. With better data, we might finally start to uncover the truth about these mysterious worlds. But until then, superpuffs remain one of the biggest cosmic enigmas. They are strange, they are unexpected, and they challenge the very limits of what we think is possible in planetary science. Every time we think we have them figured out, new discoveries force us to rethink our assumptions. They remind us that the universe is full of surprises, and that sometimes, the most puzzling questions lead to the greatest breakthroughs. The mystery of superpuffs is far from solved. But one thing is certain: as long as these strange, low-density worlds continue to defy explanation, they will keep astronomers looking up at the sky, searching for answers, and pushing the boundaries of what we know about planets, stars, and the very nature of our universe. Superpuffs represent more than just a quirky category of exoplanets. They challenge the very foundation of planetary science. Their existence forces us to reconsider what we thought we knew about the formation and structure of planets. As astronomers refine their observational techniques and develop new theories, they are beginning to realize that these puffy worlds might hold answers to deeper cosmic mysteries, possibly even reshaping our understanding of how planets evolve over time. One of the most perplexing aspects of superpuffs is the question of their atmospheric retention. Given their extraordinarily low density, these planets should struggle to maintain their thick gaseous envelopes, especially if they orbit close to their host stars. Intense stellar radiation should strip away their atmospheres over time, yet many of these planets have retained their puffed-up nature for billions of years. This raises a critical question: what mechanisms allow superpuffs to hold onto their massive atmospheres despite their weak gravitational pull? One potential explanation involves magnetic fields. On Earth, our planet's magnetic field protects us from solar wind, preventing our atmosphere from being gradually eroded away by the sun's radiation. If superpuffs have unexpectedly strong magnetic fields, they might be able to retain their atmospheres longer than expected. However, generating a strong magnetic field usually requires a fast-spinning, molten core, something we wouldn't typically expect in such lightweight planets. If superpuffs do have strong magnetic fields, it could mean that their interiors are far stranger than we currently imagine. Another possibility is that these planets are continuously replenishing their atmospheres. If a superpuff has a substantial internal reservoir of volatile gases, such as hydrogen, helium, or water vapor, it might be able to replenish any atmospheric loss over time. Volcanic activity, cryovolcanism, ice volcanoes, or even deep-seated chemical reactions could release gases from the planet's interior, keeping the atmosphere inflated. This would suggest that superpuffs are geologically active, which raises even more questions. What kind of geological processes could sustain such activity? Could these planets have subsurface oceans or layers of exotic materials that we haven't even considered? The idea of subsurface oceans is particularly fascinating because it brings us back to the question of habitability. If a superpuff contains a thick, insulating atmosphere, it might be able to trap enough heat to maintain liquid water beneath its surface, even if it orbits far from its star. This opens up the tantalizing possibility that some superpuffs might not just be strange worlds, but potentially habitable ones. However, given their low gravity and extreme atmospheric conditions, life on a superpuff would have to be radically different from anything we know on Earth. Some astrobiologists have speculated about the possibility of life existing in the upper atmospheres of gas giants, where stable conditions could exist in floating cloud layers. If this is true, then superpuffs, with their incredibly low density and thick atmospheres, could provide an even more suitable environment for such exotic life forms. Could there be microbes or even complex organisms drifting in the gaseous layers of a superpuff? Could these planets harbor floating biospheres where life exists in ways we've never imagined? Another major question is how superpuffs formed in the first place. Our current models of planetary formation struggle to explain how such large, low-density worlds could come into existence. One possibility is that they formed much farther out in their star systems and later migrated inward. If a superpuff originally formed in a cold, distant region of space, it might have accreted large amounts of volatile materials, such as hydrogen and helium, which later expanded as the planet moved closer to its star. This could explain their bloated nature, but it also raises new challenges. how did they migrate without losing their atmospheres? Alternatively, superpuffs might be the remnants of planetary collisions. If two icy, gas-rich planets collided in the past, the resulting debris could have coalesced into a low-density, bloated world. This would mean that superpuffs are not normal planets at all but rather cosmic Frankenstein worlds, objects that formed from the shattered remains of other planets. If this is true, then studying them could provide unique insights into the violent history of planetary systems and the chaotic processes that shape them. The possibility that superpuffs are merely an evolutionary phase of planetary development is also intriguing. Could these planets be in the process of shrinking? Over millions or billions of years, could they gradually lose their outer layers and become denser, more typical planets? If so, then superpuffs might be a rare but temporary stage in the life cycle of certain exoplanets. This would mean that we are witnessing a brief, transitional moment in the history of these worlds, one that could teach us about the long-term evolution of planetary atmospheres. Looking ahead, future space telescopes will be crucial in unlocking the secrets of superpuffs. The James Webb Space Telescope is already providing deeper insights into exoplanet atmospheres, and upcoming missions like the European Space Agency's Aerial Telescope will focus specifically on characterizing exoplanet atmospheres with unprecedented detail. If we can obtain clearer data on the chemical compositions of superpuffs, we might finally determine whether their atmospheres are composed primarily of hydrogen and helium, or if they contain unexpected elements that could rewrite our understanding of planetary science. But even with all the technology at our disposal, superpuffs remain elusive. Every time we think we're getting closer to understanding them, new observations raise even more questions. They are a cosmic riddle, one that refuses to be easily solved. Perhaps the biggest lesson they teach us is that the universe is far more diverse and complex than we ever imagined. The discovery of superpuffs proves that our models of planet formation are incomplete, that there are still mysteries lurking in the depths of space that defy our understanding. These planets challenge the limits of what we believe is possible. They exist in a realm where science fiction and reality blur, where the fundamental rules of planetary formation seem to break down. If we can unravel the mystery of superpuffs, we might not only learn more about these bizarre worlds, but also about the formation of planets, the evolution of atmospheres, and perhaps even the origins of life itself. One thing is certain, superpuffs will continue to captivate astronomers, pushing them to ask bigger and bolder questions. And as long as those questions remain unanswered, the mystery of these strange, bloated exoplanets will keep us looking up at the stars, searching for the truth hidden in the vastness of space. Superpuffs are more than just an oddity in the vast landscape of exoplanets. They are a fundamental challenge to everything we think we know about planetary formation, structure, and atmospheric evolution. Their incredibly low density, sometimes comparable to cotton candy, makes them unlike anything in our own solar system. This means that every assumption we make based on our familiar planets, Earth, Jupiter, Neptune, may not apply to these strange worlds. And the deeper we look, the more puzzling they become. One of the biggest questions surrounding superpuffs is their internal composition. Planets with such low density should, theoretically, have thick atmospheres that take up an enormous portion of their total volume. But this immediately raises a problem. How can these planets hold onto such bloated atmospheres for billions of years? In our solar system, planets with thick atmospheres, like Neptune, have strong gravity to keep their gases from escaping into space. But superpuffs, with their low densities, shouldn't have enough gravity to retain such enormous atmospheres, yet they do. This contradiction suggests that something else must be at play. One hypothesis is that these planets have a much higher proportion of hydrogen and helium in their atmospheres than expected, which could make them puffier than typical gas giants. However, this theory runs into another issue. Hydrogen and helium are extremely light elements, and without strong gravity, they should have been stripped away by stellar radiation long ago. Yet superpuffs seem to persist. Another explanation is that these planets might have extensive cloud layers or hazes that make them appear larger than they really are. If their atmospheres contain thick, high-altitude clouds made of exotic compounds, they could scatter light in such a way that astronomers overestimate their true size. This could mean that superpuffs aren't actually as puffy as we think. They might just have atmospheres that distort our observations. However, this still doesn't fully explain how these planets formed in the first place. If we look at how planets form in general, we find yet another layer of mystery. Superpuffs are often found orbiting relatively close to their host stars, where radiation and stellar winds are strong. According to standard models, planets that form close to their stars should have much denser atmospheres, as the intense heat would either strip away light gases or compress them under gravitational pressure. Superpuffs completely defy this expectation. Their atmospheres remain inflated, as if they exist in a much colder and calmer environment. This contradiction suggests that superpuffs might have formed farther away from their stars and later migrated inward. Planetary migration is a well-known process in astronomy, where planets shift their orbits due to gravitational interactions with their star or other planets. If superpuffs formed in the colder outer regions of their star systems, they might have accumulated large amounts of volatile gases before migrating inward. But this raises yet another question: how did they migrate without losing their delicate atmospheres? Normally, a planet moving closer to its star would experience significant atmospheric loss due to the increased radiation, yet superpuffs seem to have defied this outcome. Some astronomers believe that superpuffs might have formed under entirely different conditions than other exoplanets. Perhaps these planets were born in unusually gas-rich regions of space, where they could accumulate thick atmospheres despite their low gravity. Or maybe they are the remnants of planetary collisions. If two icy planets crashed into each other in the past, their combined debris could have reformed into a bloated, low-density world. If this is the case, then studying superpuffs could give us direct evidence of ancient, catastrophic planetary events. Beyond their formation, there's another mind-bending question: could superpuffs evolve over time? Planets aren't static objects. They change over billions of years as they lose gases, experience impacts, and undergo chemical transformations. It's possible that superpuffs are simply a temporary phase in a planet's life cycle. Perhaps they start off puffy but gradually shrink as they lose atmospheric gases. If this is true, then superpuffs might not be a permanent type of planet, but rather a short-lived stage that some planets pass through before becoming denser, more conventional worlds. To solve these mysteries, astronomers are turning to advanced telescopes. The James Webb Space Telescope, JWST, is already providing some of the most detailed data on exoplanet atmospheres, and it could hold the key to unlocking the secrets of superpuffs. By analyzing the light passing through their atmospheres, JWST can determine their chemical composition, helping us figure out whether these planets are mostly hydrogen and helium, or if they contain unexpected elements. If we find that their atmospheres are filled with water vapor, methane, or exotic compounds, it could completely reshape our understanding of what these planets are made of. Another promising approach involves studying their atmospheric winds and weather patterns. If superpuffs have active weather systems, with storms or high-speed winds, it could help explain how they maintain their bloated atmospheres. If their gases are constantly cycling between their surface and upper atmosphere, they might be able to sustain their puffy nature longer than we expect. Some scientists have even speculated that superpuffs might have rings or exomons that contribute to their strange appearance, though no direct evidence of this has been found yet. Perhaps the most intriguing possibility is that superpuffs could harbor conditions suitable for life. While their extreme low density makes them unlikely candidates for Earth-like life, some researchers believe that their thick atmospheres could support floating ecosystems, similar to what has been theorized for the clouds of Venus. If these planets have stable temperature layers within their atmospheres, microscopic life could potentially exist in these regions, suspended in the air like plankton in Earth's oceans. This idea may seem far-fetched, but it aligns with the broader question of whether life can exist in extreme environments. On Earth, we've found organisms that thrive in boiling water, deep underground, and even inside nuclear reactors. If life can exist in such extreme conditions here, why not on a superpuff? If these planets have chemical reactions that resemble Earth's prebiotic chemistry, they could provide valuable clues about how life emerges in the universe. Superpuffs remain one of the biggest unsolved puzzles in planetary science. Every new observation adds another layer of complexity to their story, making them even more difficult to explain. But this is what makes them so fascinating. These planets are reminders that the universe is far stranger than we ever imagined. They challenge our assumptions, force us to rethink our models, and push us to keep searching for answers. One thing is certain: the mystery of superpuffs is far from solved. And until we unlock their secrets, they will continue to be some of the most intriguing and perplexing objects in the cosmos. Superpuffs are not just an anomaly, they might represent an entirely new class of planets, one that forces us to expand our understanding of planetary physics, atmospheric dynamics, and even the fundamental processes that shape the universe. Their existence challenges our models in ways that few other exoplanets do. While scientists have proposed multiple theories to explain them, every possible explanation seems to come with its own contradictions. This is what makes them so frustrating, yet so exciting. One of the most baffling things about superpuffs is their sheer size relative to their mass. Some of these planets are as large as Jupiter but have only a fraction of its mass. This means that their densities are staggeringly low, so low that they seem to defy the very physics of planetary formation. Imagine a balloon the size of a planet, but so lightweight that it barely exerts gravitational force on itself. How could such a world form? And how could it maintain its structure without collapsing or dissipating over time? To put this into perspective, let's take a closer look at one of the most famous superpuffs, Kepler-51d. This exoplanet, located about 2,600 light-years away, is roughly the size of Jupiter but has an estimated density comparable to that of cotton candy. If you could somehow stand on this planet, which is unlikely given that it's mostly gas, you would weigh much less than you do on Earth, and you might even be able to move through the atmosphere as if you were in a dense fog. The leading explanation for Kepler-51d and other superpuffs is that they have incredibly thick atmospheres made up of light gases, such as hydrogen and helium. But this immediately raises another question: why hasn't this gas escaped into space? Planets with weak gravity typically struggle to hold onto their atmospheres, especially if they orbit close to their stars. Yet superpuffs seem to retain their bloated atmospheres for billions of years. This suggests that either our understanding of atmospheric retention is flawed, or that superpuffs possess some unknown mechanism that allows them to defy expectations. One possibility is that these planets have unusually strong magnetic fields that protect their atmospheres from being stripped away by stellar radiation. On Earth, our magnetic field acts as a shield, preventing solar wind from stripping away our atmosphere. If superpuffs have a similar but much stronger magnetic field, it could help them hold on to their gases even in environments where they should be losing them. However, generating a strong magnetic field usually requires a fast-spinning metallic core, and it's unclear whether superpuffs have the internal structure necessary for this. Another theory suggests that superpuffs formed much farther from their stars, in cold regions where gases could accumulate more easily, before migrating inward. In this scenario, they would have started as icy worlds with thick hydrogen-rich atmospheres, similar to mini-Neptunes. Over time, as they moved closer to their stars, their icy cores could have evaporated, leaving behind only the bloated gas envelopes we see today. But this explanation also has problems. Migration tends to be a violent process, and many planets lose their atmospheres during such shifts. There's also the possibility that we're simply misinterpreting the data. Our current methods of detecting exoplanets rely on indirect measurements, such as the way a planet dims its star's light when it passes in front of it. If superpuffs have unexpected atmospheric properties, such as high-altitude clouds or unusual scattering effects, our measurements of their size could be incorrect. They might not be as puffy as we think. They could simply be tricking our instruments into overestimating their radii. To solve these mysteries, astronomers are looking toward the James Webb Space Telescope, JWST, which has already started to revolutionize our understanding of exoplanet atmospheres. With its ability to analyze the chemical composition of distant planets, JWST could help us determine exactly what superpuffs are made of. If their atmospheres contain large amounts of water vapor, methane, or other molecules, it could help us determine how they formed and how they've managed to remain so puffy for so long. Another key piece of the puzzle is understanding how superpuffs interact with their parent stars. Some of these planets orbit extremely close to their stars, where intense radiation should be stripping away their atmospheres. If we can observe atmospheric loss in real time, it could give us insights into whether these planets are in the process of shrinking, or if they have mechanisms preventing them from losing their gases. One particularly interesting aspect of superpuffs is their potential for atmospheric escape. In theory, if their atmospheres are as bloated as we think, they might be slowly leaking gases into space, forming enormous, comet-like tails. If we can detect these tails, it could confirm that superpuffs are in the process of evolving into denser planets. But so far, no such tails have been observed, suggesting that these planets have some way of holding onto their atmospheres despite their weak gravity. Another wild possibility is that superpuffs are actually the remnants of failed stars. In the earliest stages of star formation, some objects don't accumulate enough mass to ignite nuclear fusion, and instead become brown dwarfs or massive gas planets. If superpuffs are failed stars that never fully formed, they might have unusual compositions that explain their strange properties. However, this would require them to have formed in a completely different way than typical planets, which raises even more questions. Some scientists have even speculated that superpuffs might not be planets at all, but rather massive collections of debris held together by weak gravitational forces. If these planets were formed from the remnants of destroyed worlds, their low densities could be explained by the fact that they are essentially planetary rubble clouds, loosely bound together by gravity. This could also explain why they appear so large. If they are composed of loosely packed material, they could have enormous radii without actually being solid objects. And then there's the most mind-bending possibility of all. What if superpuffs are something entirely unknown to science? The universe has a habit of surprising us, and every time we think we understand how planets work, we discover something that forces us to rethink our models. It's possible that superpuffs represent a stage of planetary evolution we haven't seen before, or that they contain exotic forms of matter we don't yet understand. Whatever the truth may be, superpuffs are a perfect example of why space exploration is so exciting. They remind us that the universe is far more complex and strange than we ever imagined. They challenge our assumptions, force us to push the boundaries of our knowledge, and drive us to keep looking deeper. As telescopes like JWST continue to gather data, we may finally start to uncover the secrets of these bizarre worlds. But until then, superpuffs will remain one of the most perplexing and fascinating mysteries of the cosmos. A reminder that, no matter how much we learn, the universe will always have more surprises waiting for us. Superpuffs are not just a curiosity, they could be key to understanding planet formation as a whole. If our current models of planetary evolution cannot explain these ultra-low-density worlds, then we may need to rewrite some of the fundamental principles of how planets grow, how they hold on to their atmospheres, and even how they interact with their stars over time. One of the biggest questions surrounding superpuffs is whether they are a temporary phase in planetary evolution, or if they can remain in their bloated state for billions of years. If they are temporary, this would suggest that we have caught them at a rare moment in their development. Perhaps they are slowly losing their atmospheres and will eventually shrink down into denser planets like Neptune, or even Earth-like worlds. If they are permanent, then there must be a stabilizing factor that allows them to remain puffy despite their weak gravity and exposure to stellar radiation. Understanding superpuffs could also help us refine our search for habitable exoplanets. If these worlds are found to have thick, stable atmospheres that protect them from stellar radiation, it could mean that other, denser planets with similar atmospheric properties might also exist. This would have huge implications for astrobiology, as it would expand the range of planets that could potentially support life. But what if superpuffs have conditions that make them even stranger than we currently realize? Some scientists have proposed that these planets might have exotic atmospheric chemistry that is completely different from anything we've seen before. If their thick gas envelopes contain unusual elements or compounds, it could explain why they remain so inflated. There's even the possibility that they contain substances that do not exist naturally on Earth, materials with properties that defy our current understanding of physics. One of the most extreme theories suggests that superpuffs could be composed of a high concentration of dark matter, an invisible form of mass that makes up most of the universe but remains undetected except through its gravitational effects. If these planets somehow contain or interact with dark matter in an unknown way, it could provide an entirely new avenue of research in both planetary science and cosmology. However, this idea remains speculative, as there is no direct evidence linking dark matter to planetary formation. Another mind-boggling possibility is that superpuffs are actually failed gas giants that never fully formed. In standard planetary formation models, gas giants like Jupiter and Saturn start as rocky or icy cores that rapidly accumulate massive amounts of hydrogen and helium from the surrounding protoplanetary disk. If something interrupted this process, perhaps a sudden change in the disk's composition or a nearby star's gravitational influence, it could have left behind planets that started forming as gas giants but never finished, leaving them in an unstable, bloated state. The problem with this theory is that superpuffs seem to be stable over long periods of time. If they were truly unstable remnants of failed gas giants, we might expect to see evidence of them shrinking, dissipating, or even losing their atmospheres in real time. Yet, as far as we can tell, they remain intact, orbiting their stars without any signs of rapid change. Some researchers have also suggested that superpuffs might be evidence of completely new planetary formation pathways. In our solar system, planets formed from the gradual accumulation of dust and gas, either becoming rocky terrestrial worlds or massive gas giants. But what if there's another way to form planets? One that allows for ultra-low-density worlds to exist in a stable state. If this turns out to be the case, it would mean that the diversity of planets in the universe is even greater than we ever imagined. One of the key mysteries that astronomers are trying to solve is whether superpuffs have thick cloud layers that make them appear larger than they really are. If these planets have high-altitude haze or cloud cover, it could scatter light in such a way that our instruments overestimate their size. This would mean that they are not actually as puffy as we think, but rather that their atmospheres create an optical illusion that makes them look much larger than their actual physical size. To test this idea, astronomers are using the James Webb Space Telescope to analyze the atmospheres of superpuffs in detail. By measuring how light filters through their atmospheres as they pass in front of their stars, scientists can determine what gases are present and whether thick clouds or hazes are playing a role in their strange properties. If they find that superpuffs have clear atmospheres with no unexpected cloud cover, then their bloated nature will need to be explained by another mechanism. Another challenge in understanding superpuffs is determining whether they contain solid cores. In traditional planetary models, gas giants like Jupiter and Saturn have dense cores made of rock and ice, surrounded by thick layers of hydrogen and helium. If superpuffs lack a significant core, it could help explain their extreme low density. However, if they do have solid cores, then something else must be responsible for keeping them so inflated. One hypothesis is that superpuffs have incredibly thick layers of volatile gases, such as methane, ammonia, or water vapor. These substances have lower molecular weights than hydrogen and helium, which could contribute to their extreme puffiness. If this is the case, it could mean that superpuffs are actually water-rich worlds with deep, dense atmospheres that give them their oversized appearance. Another possibility is that these planets are still in the process of cooling and contracting. Young planets tend to be hotter and more inflated due to the residual heat from their formation. If superpuffs are relatively young, they might still be radiating heat from their interiors, which could be preventing their atmospheres from collapsing into a denser state. However, this explanation doesn't hold up for all superpuffs, as some of them appear to be billions of years old, long past the period where they should have cooled and contracted. This raises yet another question: could superpuffs have internal heating mechanisms that prevent them from shrinking? On Earth, geothermal activity from radioactive decay keeps our planet's interior warm. If superpuffs have unusual internal processes that generate heat, perhaps through tidal forces from their stars or interactions with nearby planets, it could keep their atmospheres in a bloated state for far longer than expected. Superpuffs also challenge our understanding of planetary atmospheres in extreme environments. Some of these planets orbit very close to their stars, where they are bombarded with intense radiation. Normally, we would expect their atmospheres to be stripped away over time, yet they remain bloated and intact. If we can figure out how they manage to hold onto their atmospheres, it could provide insights into atmospheric retention on other planets, including potentially habitable worlds. Even more intriguingly, some scientists believe that studying superpuffs could provide clues about the early atmospheres of planets like Earth. If these planets started out with thick, puffy atmospheres before evolving into denser worlds, it might help us understand how planets transition from one stage to another. As we continue to observe these strange worlds, new data could completely upend our current theories. Perhaps superpuffs are only the tip of the iceberg, and there are even more bizarre exoplanets waiting to be discovered. Planets with densities lower than air, planets that defy gravity, or planets with atmospheres so massive that they extend for millions of kilometers into space. One thing is certain, superpuffs remind us that the universe is full of surprises. Just when we think we have a solid understanding of planetary formation, something like this comes along and forces us to reconsider everything. They are a humbling reminder that space is still a vast, unexplored frontier, filled with mysteries that challenge our knowledge at every turn. As telescopes become more advanced and our ability to study exoplanets improves, we may finally get answers to the questions surrounding superpuffs. But until then, they will remain one of the most puzzling and fascinating mysteries of the cosmos, strange, improbable worlds that defy our expectations and invite us to keep looking deeper. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.